This is a video I've been looking forward to making for quite a long time. I want to talk about some stuff I've been thinking about over the last few months, and really I want to center this around a simple question. What is behind geometry? Okay, so this is a somewhat vague question, but I think it's a very, very interesting one. So what do I mean by that? Well, we know that mathematics has all these abstract rules, and we can sometimes use those abstract rules to give rise to things in geometry. Okay, this is one of the main things that kind of happens in mathematics. Usually we ask some kind of a question, and very often in answering that question, we find that there are some sort of geometric shapes or geometry-like structures that are somehow behind the kind of problem we're thinking about. And this gives rise to this kind of idea that many mathematicians have that there's some sort of a Platonic realm of shapes, which is somehow governing how things in this reality work. Okay, so there are various ways you can look at geometry, and you can kind of look at it in a certain way where you kind of feel like, okay, there's some other kind of abstract maths which is behind this. So a really obvious example of this is using networks or graphs. Okay, so if I draw a triangle, I can draw three dots and I can link them with lines. But in graph theory, we only really care about how the dots and lines are connected up. We don't really care about exactly how they are positioned in space. So if to a graph theorist, these two shapes are the same because kind of topologically or how they are connected, they look the same. So a graph theorist can look at geometry, and then they can kind of brush away details to do with like exactly where the things are placed and only focus on connectivity. And they can say, okay, that's something that's actually behind geometry. That's something that's more fundamental. And from certain perspectives, this is true. Okay, so for example, you can ask a question like, what are the most regular 3D solids? And you get answers like the cube, the tetrahedron, and so on. There are these five platonic solids, and then you can ask, okay, well, why are there only five? And one way you can answer this is to look at the problem in terms of graph theory. Okay, so it turns out that a graph theorist can sort of prove that there are only five platonic solids just by thinking about those graphs. They don't have to worry about the spatial structure. And this kind of bolsters this perspective that actually the kind of spatial positions of things are not as fundamental as the way things are connected together. But that's a matter of perspective. And a geometer might say, well, a cube or a tetrahedron or something is more fundamental than its graph because it has spatial structure, and that spatial structure is naturally kind of part of the parcel. Okay, so in this sense, you could say that graph theorists are not really dealing with the whole plethora of stuff that's going on. They're kind of being ignorant of geometric positionings of points and so on. So what do we do? Well, we can step back. We can say, oh, it's all a matter of perspective. Every area has their own way of looking at things, etc., etc. But you know, this can sometimes be a bit of a like it's a nice standpoint to keep everyone happy, but I think the truth of mathematics is that there are certain ways of looking at things which just give much, much more insight into their true nature. So, so let's ask again, what lies behind geometry? Okay. Well, I would say that strictly from a sort of mathematical point of view, you could argue that nothing really lies behind geometry. Like that's not how the mathematical landscape is structured. It's not like there's like one thing that like comes before another necessarily. No, no. All the mathematical structures are all defined simultaneously. They all exist all together at the same time, and there's no real starting point. You can look at it like that, but you know, that's a sort of philosophical position. Maybe not a particularly useful one, to be quite honest. And I'm not even sure if it's really correct. I do think, having been a mathematician for quite a long time, that, you know, there are certain places where it's a really good idea to start and look at a subject in terms of, things, basic things that you can take as primary. And sometimes, if you're lucky, you can do that and you can really see that there's a sort of like a causal chain so that you can really just start with some simple ideas and turn some sort of a crank and generate lots and lots of interesting structures. So people who have followed my YouTube channel, especially in the early days, will know that I'm really into this kind of approach to mathematics, the kind of a little bit like this sort of Stephen Wolfram new kind of science approach where you say, well, let's start with something extremely simple, some kind of simple rule, let's run it and let's see what happens. And let's try and find rules that generate interesting structures that we care about. Okay, so this I think is a really, really healthy approach to mathematics. And we can then again ask, what lies behind geometry? Okay, so we have this idea now that we might start with some simple rules, and then we might generate some sort of patterns. And again, we see this everywhere in mathematics and physics. You could say that a lot of physics is about really discovering these simple rules, things like force equals mass times acceleration and so on, which, if we look at the computational consequences of those, we're going to see all these patterns in the real world. And I'm asking now, is there something similar to this that's happening for geometry? And of course, the answer is yes. So anybody who's played around with dynamical systems or physics or computational processes will know that there's a huge plethora of different simple rules that can lead to patterns, and those patterns are often in the form of geometric shapes. Okay, so this is a really sort of simple but really important thing to bear in mind, I think. Just the simple idea that we can generate all sorts of patterns by following these simple rules. I think this is so important because, like, we shouldn't be sort of arrogant about what's possible. Okay, I believe that a lot of people, when they've been doing mathematics long enough, they start to get some sort of feeling like they really understand what kind of patterns can be made by what kind of rules. And I think this is folly. I think that the truth of it is that this sort of world of computation or world of extracting patterns from rules is extremely rich and can be extremely complicated. Okay, so you can find things like Conway's Game of Life or all sorts of setups where you could have relatively simple rules generating extraordinary, interesting, and difficult to predict kind of patterns. So this is certainly one way that we can get kind of underneath geometry in some sense, right? We can think about simple rules that give rise to the patterns of geometry. And again, people who followed my channel for a long time will know that this is something I'm really interested in. And so back in the day, I did quite a lot of research along these kind of lines, looking at different simple systems and seeing what kinds of structures they can produce. Here's a piece of research I was quite happy with. I wrote this paper called Complex Networks from Simple Rewrite Rules. And the idea is that we consider a graph or network where every edge is red, green, or blue, and there's one red, one blue, and one green edge touching every vertex precisely. So this isn't really the subject of today's discussion, but just to recap this briefly, the idea is that we start off with some network where every vertex just has one red edge, one green edge, and one blue edge connected to it. So everything has three connections. And then we have a special sort of distinguished vertex, which we call the writer vertex. That's this black dot here. And we start off with some shape, let's say a cube, and then we just have these rewrite rules. And these rewrite rules just tell us, how the system works. So they say, well, if we look at the neighborhood around the writer vertex up to a couple of connections away, and we look at the shape of that, then we can see which of these configurations that corresponds to, and then we can apply the appropriate rewrite rule. So for example, this first rewrite rule here says, make a triangle where the writer vertex currently is, and move the writer vertex along a blue edge. Okay, so we can apply this rule, and you can see that it changes the cube into this other shape. So we have lots and lots of these kind of simple rules that can generate networks. This is somewhat akin to how a Turing machine works, except that we don't really have a notion of external state. Everything's kind of encoded on the level of this kind of colored trivalent network, if you like. Now, the point is that if we look at what's possible now, say just starting with a cube and from different rules, we can generate structures of immense complexity and interest, okay? So this is one that I really like. When we run the system with these rules, we can run it for as long as we like, starting for a cube, and it just seems like there's extremely complex behavior that just persists. And this is sort of complex behavior which is generated kind of intrinsically from these rules. So this is really interesting from a scientific perspective, although now we're sort of going a bit away from this central question that I keep asking, which is what lies behind geometry? So I just thought I would mention this possibility of using graph rewrite systems or string rewrite systems. And there's also something called reproducing graphs, which I've looked at before. But I'm just trying to sort of mention that there's a whole plethora of different simple rules which we might study and wonder if those give rise to geometry. Okay. Now I want to back up a little bit, because I do believe that this question of what lies behind geometry is not only a mathematical question. I think it's also a question in physics. So if you really want the best possible setup for theoretical physics, it's my belief that that kind of setup will have space as something which is emergent. Okay, what I mean by that is that you won't start your setup by saying, okay, let's assume that we have 3 dimensions of space, 1 dimension of time, and blah, blah, blah. No, no. I think that if you do it right, you can probably get it to work so that you don't put any space in. So maybe it works a little bit like these systems where you just start off with some simple kind of seed structure and some simple rewrite rules, and then you get a topological notion of space, and that sort of gives rise to the actual space that we think about. Because if you imagine a big network where things are connected together and you have little signals which are firing between the stuff that is connected together, you could imagine that that information is only sort of topological, but if we're living in such a structure as sort of macroscopic things, we might start to imagine that it's actually in a kind of rigid spatial pattern, because it's only the local interactions which we're aware of, and they essentially act as if the thing's in a rigid setup. So okay, complex patterns from simple rules. That's one possibility, right? But what other possibilities are there? Well, we know that geometry is very related to the idea of symmetry. So obviously, if we have any kind of geometric shape, we can ask about what kinds of symmetries it has. Now, the fact that it's possible to ask about symmetries for all sorts of shapes and also other things in abstract math, I think that's a kind of clue that maybe this idea of symmetry is at least as fundamental as the idea of geometry. Okay, now this is a perspective which I think one has to see enough stuff, and then kind of, this is my opinion of it, like that if you've seen enough math, you start to like think that symmetry is more and more important. Okay. And like I started off doing theoretical physics, I came to mathematics later. It was a long time until I really looked directly at group theory. And I kind of, for a very long time, had a bit of a feeling that it wasn't quite the right way to look at things. And I think it's because I didn't encounter the right kind of group theory or the right kind of perspective on this subject. Because I do think that group theory and abstract algebra have kind of grown independently, let's say. And I don't really mean that as a compliment necessarily. I do think that um, certain mathematical disciplines, if they're allowed to just develop on their own for long enough, they can start to, you know, think about a lot of topics which are maybe not necessarily as closely related to really fundamental stuff as one would want. What I mean is basically that, like, I love abstract math, but if you go too far, you can just basically lose sight of the ground. And I think this is why it's often a really good idea to come back to some really basic questions like, you know, what lies behind geometry or what lies behind physics as a way to sort of reorient ourselves and find the right kind of structures. So I do believe in the end that this connection between geometry and symmetry is one of the most fundamental. And the thing is that here, this is in a way a bit more magical even than the sort of patterns from simple rules perspective from before, because if we can really get a handle on kind of how geometry emerges from symmetry, well, that's not only going to help us to understand all the different spatial forms that are possible, it's also going to help us to understand the different kind of transformations of space. And we're going to see that those really, well, I think that those really underlie our number systems, even. And so I think what we actually get if we look at things in the right way is, I mean, I'm going to say it almost like a theory of everything, really, where we just have some very kind of simple code which lies behind these symmetries. And if we understand that code and how to read it and how to, you know, what it really means, not only do we see all geometry emerging from that, we see our number systems, we see our you know basic ways of thinking about spatial things. It all kind of emerges from a central point. Okay, so this I think is extremely exciting and basically corresponds to what is called Coxeter groups. So we're going to understand what Coxeter groups are and how they give rise to geometry, essentially. And okay, I don't have as much time to make YouTube videos as I used to have. So what's following, there might be some aspects of it that are a bit rushed because I just had to get everything sort of out, and I don't have the time to keep refining these things like I used to have. And so I've tried to keep the following content kind of self-contained and also kind of grounded in algorithms. Okay, so at the end of the day, I'm especially interested in telling you about an algorithm which I wrote, which sort of takes these Coxeter groups and produces the corresponding kind of geometric forms. So I want to explain that and a few other things, and I hope you'll enjoy it. Now, I do have a longer video called Perfect Shapes. So I'm going to try and make this video self-contained, but if you find yourself getting lost, then I would encourage you to have a look at that other video on perfect shapes first. Maybe if you just watch the first hour or two of that, it'll put you in a really good position to understand the rest of this stuff. Okay, so the central thesis here is that we can understand about shapes and geometry in a very fundamental way by understanding about Coxeter groups. But what kind of shapes are we really talking about here? Well, really, um, I could give a rather general answer, but let me say something that's more um, thought-provoking, which is that we're going to really focus upon things which are called regular polytopes. So, what is a regular polytope? Well, think about an equilateral triangle that has the feature that every vertex looks like every other vertex, and similarly, every edge looks like every other edge. A square or a regular pentagon, they also have this feature that any part of them looks similar to any other part of the same dimension. The same is true in three dimensions for things like this dodecahedron or the cube, these so-called platonic solids, which have vertices, edges, and faces, but they have the feature that every edge looks the same as every other edge, and similarly for faces or vertices. And so we can imagine the same kind of idea extended into higher dimensions as well. So, for example, here is a picture of a four-dimensional hypercube. So, in addition to having vertices, edges, and faces, for example, this would be a face, well, this also has three-dimensional cells. For example, there's a cube-shaped cell in the middle of this, and then there are six of these cube-shaped cells around the outside of that, and then the very outside of this shape is considered to be the eighth and final three-dimensional cell of this four-dimensional cube, also called the tesseract. So this is a four-dimensional version of a regular polytope. So the word regular polytope takes this idea of platonic solids and generalizes it to a general number of dimensions. And there are very interesting different kinds of regular polytopes. And really, that was the focus of my video on perfect shapes specifically. Um, but in fact, but in fact, Coxeter groups kind of go beyond regular polytopes. They also discuss other things. So a good way to think of a good way to think about this subject, I think, is as follows. Think about bees and honeycombs and how they can tile the plane with hexagons. So this is a really fundamental thing, like just in reality, okay? The sort of if you get into Lie groups and things, a lot of deep structure kind of is related to the fact that there's only a few ways to tile the plane. Okay, so you can tile the plane with hexagons like bees do um, in their honeycombs. You can also tile the plane with squares, or you can tile it with triangles. Actually, the way you tile the plane with triangles is kind of hidden in this picture. Because if we just sort of dualize this shape, in other words, put a vertex in the middle of each face in this case, well, we get a triangular um, tiling of the plane. So basically, there's only three possible ways to tile the plane with regular shapes. You can use triangles, you can use squares, or you can use hexagons. So what? Well, what if you tried to use pentagons? Okay, so imagine you got a load of pentagons and you tried to slot them together so that you would sort of fill two-dimensional space. Well, in a way, what would end up happening would be that that pattern would end up closing up to form a sphere and we'd get a dodecahedron. So we can think of a dodecahedron as a sort of tiling of the sphere as opposed to the plane. And so, in this sense, you can think of a regular polyhedron as a tiling of the sphere. It's just that when you're tiling a sphere with regular polygons, you only need finitely many because the sphere is going to close up. Um, so that would be the sort of inward curved case, but there would also be a hyperbolic case um, where you would be tiling something like a saddle shape
Or, you can think of these Escher pictures and things, which are showing this sort of Poincaré disk, which shows you that um, if you're working with hyperbolic space, you can tile things, for example, so that um, you have seven triangles meeting at every point, as opposed to um, this picture here, where we'd end up with six triangles um, meeting at every point. Is similar pattern to what you find um, when you push pennies together on a table. Um, but you know, in hyperbolic space, you can have other things. And the thing is, though, these Coxeter diagrams, basically, or variants of them, that kind of idea applies throughout all of these cases. All right. So, in fact, we can think about infinite tilings, for example, this hexagonal tiling, and there'll be a corresponding way to talk about that in terms of these Coxeter diagrams as well. And so this is not just um, something that's only of interest to geometers who have, old-fashioned tastes in these regular polytopes. The Coxeter diagrams and the sort of related ideas to do with Dynkin diagrams and ADE graphs, ADE phenomena, really are very close to the middle of maths in a sense. And in my view, a lot of this stuff with the Coxeter diagrams is um, giving it's giving a clean way to introduce lots of mathematical structures. So okay, let's go through a really really quick introduction to higher dimensional space, as much as we'll need. So we can have a zero-dimensional hypercube. That's a point. A one-dimensional hypercube is a line. A two-dimensional hypercube is a square. Now, notice that we can get the square by taking the one-dimensional hypercube and then moving it in a direction perpendicular to the directions that we already have. And that gives us this square. So you can sort of get a square by taking a line segment and sweeping it downwards. Now, if we get that square and we do similar, we can get a cube, which is a three-dimensional hypercube. So we take our square and then we move it in a new direction, which is perpendicular to the directions that we already have. And that's going to end up sweeping out to cube. Now you can think of a cube as a polyhedron that has vertices, edges, and these faces here. And so this would be an example, aka a polyhedron, the cube. Now, if we take the cube, then we can get the four-dimensional hypercube by applying the same kind of idea. We take our original cube, we move it in a direction perpendicular to the ones that we already have, and the sort of shape that gets swept out by that is called the hypercube. This hypercube, in addition to having vertices, edges, faces, now we have these volumes as well, which themselves are cubes, and there are eight of those. So we saw another depiction of a hypercube up here. And we could go on into higher dimensions. Okay, so that's one thing. The other thing we're going to need is this idea of so-called Schlafly symbols. So I'm just going to go through this very quickly. If we have a polygon, for example, this square, we look at how many sides it has, and that gives us the Schlafly symbol. So the Schlafly symbol for a square is a 4 in curly brackets. So okay, that's the deal for the square. What about this polyhedron here? Well, to get the Schlafly symbol for that, first we look at what the faces look like. They're squares. So we put 4. and then we say how many of these faces are touching a particular vertex, and the answer here is 3. So the Schlafly symbol for the cube is 4, 3. So more generally, if we have a polyhedron which has the Schlafly symbol p, q, that means that the faces are pgons and there are q of them meeting every vertex. Now, for the tesseract here, the hypercube, the Schlafly symbol for this is 4, 3, 3. Now, the first two numbers are telling us that the cells are cube-shaped because 4, 3 is the Schlafly symbol for the cube. And the final number is telling us how many of these 3 cells there are around a particular edge. So if we pick a particular edge, then we count how many 3 cells are touching that edge. The answer is 1, 2, 3. Okay, so that's telling us that final information. And since we know that this is this regular polytope, once we know the sort of shape of the cells and how many of them are touching the edge, that tells us what we need to know. So more generally, um, for a regular polytope that's 4-dimensional, like this tesseract, the Schlafly symbol PQR would denote that. And what this means is that the 3 cells are PQ. So that's a Schlafly symbol for a polyhedron, telling us the shape of the cell. And then there are R of them touching an edge. Okay. So that's the basic idea of Schlafly symbols. They go on in higher dimensions. Um, I discussed this in much more detail in the perfect shapes video. But here's the really cool connection, okay? Because now we're going to get to Coxeter groups, but now you know about Schlafly symbols, I can kind of tell you loads of Coxeter group stuff without having to explain any of the technicalities because I can say this. Suppose we have, let's say, a 4-dimensional regular polytope. So it has a Schlafly symbol like P, Q, R. Now, it turns out that this is the same as something else. And this something else might not mean anything yet, but I'm going to explain the meaning of this in due time. But it means the same as this. Okay, so what is this funny thing that I've just drawn at the bottom here? Well, basically, this is a Coxeter diagram, also called a Coxeter graph. Okay. And basically, it's telling us about the symmetries of this regular polytope here. Now, we're going to see how all this works later, but that's the basic idea. Now, what is this? Well, this is basically describing something called the Wythoff construction. Now, you're going to have to be patient with me with this word Wythoff. I don't know why. It's some kind of flare up of dyslexia or something. But whenever I see this guy's name, it confuses me, and I think I spell it wrong and I say it differently. And I apologize in advance because I have great respect for this mathematician's work, but for some reason, my brain can't seem to get working with pronouncing this guy's name properly or spelling it correctly. So anyway, this Wythoff construction, um, is the main thing that I want to talk about. And basically, it's a way that we can, once we have this Coxeter group corresponding to this Coxeter diagram, we can use it um, basically to work something like a kaleidoscope where we apply the symmetries we have to a certain point in space and see how that gets reflected around. And that gives us the vertex set of our regular polytope. So this is the main thing that we're kind of interested in, but it's much deeper than this. It applies in a very general way. And we're going to get into this. Um, but but the main point that I want to get across is as follows. Okay. It turns out basically that you can use a Coxeter diagram with a ringed node. Okay, so I might refer to these as vertices or nodes, but we're going to sort of ring or circle one of these nodes, and we're going to use such a diagram, and this will correspond, at least sometimes, to a regular polytope. Okay, so this is basically what we're going to do. And I know that I haven't explained what these Coxeter diagrams are properly yet, and really this is the sort of challenge of this video, but we're going to get there. But let me just show you basically how this works. So, say you give me a regular polytope. So, for example, it might be a cube. I'll draw it like this. So, the faces are foregons, and we have three of those faces meeting every vertex. So, the Schlafly symbol for the cube is 4,3. And the corresponding Coxeter diagram is this. Okay, similarly for the hypercube, the Schlafly symbol was 4, 3, 3, and the corresponding Coxeter diagram is this. For a square, the corresponding Coxeter diagram is this. Now, again, there's a little bit of a subtlety here, which is that these are actually more than Coxeter diagrams. These are Coxeter diagrams with a circled node, and that means we're talking about a Wythoff construction, which is involving this kaleidoscope and so on. And so we're going to understand how all this works. Now, to begin with, let's take a look at the triangle. And we're going to look at that example, but bear in mind that the whole discussion works equally well, no matter how complicated the regular polytope is. And in fact, um, we can go beyond regular polytopes and into these other scenarios about these honeycomb shapes. So, a honeycomb in general, when I talk about honeycombs, I don't just mean the hexagonal tiling. I mean, in general, we have n-dimensional space, and we take a particular polytope, and we can use that regular polytope to fill that space with in a kind of infinite pattern. So we could also discuss those, and we could also discuss tilings of hyperbolic space as well. So um, there's we could expand on the discussion a lot, but we're really going to focus on um, on we're gonna start by looking at things like triangles and n-dimensional simplexes. So maybe that's the final thing I should say for a sort of primer, because this is also very important. So another really important family of regular polytopes, we start with a zero-dimensional simplex, that's a point. One-dimensional simplex is a line. To get a two-dimensional simplex, we take our line and we add a new point that's connected to everything. And then the three-dimensional simplex is the tetrahedron. And then to get the four-dimensional simplex, we take that and we add a new point that's connected to everything that we had before. So now we have the four-dimensional simplex, and this is also called the five cell because in addition to having vertices, edges, and faces, like this guy does, the five cell also has five tetrahedron shaped three cells. And so to write the Schlafly symbol for it, remember for a regular polytope PQR, this is the shape of the three cell, and this is the number of three cells touching an edge. So in this case, the three cells themselves are tetrahedra, have Schlafly symbol 3, 3, because we're talking about three gons, and there's three of them touching a vertex. And then the number of tetrahedra that are touching an edge is also 3. So that's the Schlafly symbol for this five cell here. And so when you see a Coxeter diagram like this, with that vertex ringed, well, that means a five cell. Also, I should say that it's a common practice not to bother writing the number 3 when you see Coxeter diagrams. It's like threes appear so much that mathematicians have applied a convention of just not writing threes sometimes. So if you see a Coxeter diagram where the edges are not labeled, you should label them with threes because that's what that's shorthand for. So given all that, let's now take a look at the triangle, which is this. And let's try and understand where these Coxeter groups really come from. Now, when I introduce it, it'll look more like this. But the colors you don't really have colors in Coxeter diagrams. I might add them for the sake of making things look clearer.
So what I want to convey is how geometric shapes, such as this triangle, can arise from symmetries. But it's going to be easiest to explain how things work the opposite way around to begin with. So let's suppose we have some geometric shape, some regular polytope, so everything's really symmetric. And the question is, how can we understand the symmetries of that shape? And there's just such a beautiful answer to this question that it's a really great place to begin in this subject. So basically, to answer this question, we proceed as follows. We pick any vertex that we want, and we call that vertex O0. Now, we can do this for any regular polytope. So we could be working with some 17-dimensional hypercube, but I'm just going to talk about the triangle because it's simpler. But remember, you can do the same thing in lots of other cases. Okay, so step 1, pick a vertex and call it O0. Step 2, pick any edge that's touching that vertex and call the center of that edge O1. Okay, next step, pick any face that's touching that edge and call the center of that O2. And if we were working in high dimensions, we would carry on and we basically go as far as we can go. So the next step would be to take a three-dimensional cell that has this as a two-dimensional boundary, and we call the center of that O3, and so on. So, okay, we can form these points. All right, but what's the point though? How does having these special points benefit us? Well, so the next step
So the next step is to use these points to do something. Okay, so we have a red point, and what we're going to do is draw a red line through all the points except the red points. We can do similarly for the blue. So we draw a blue line through the red and the green points. We could do similar for the green, but I'm not going to do that. You can see that the green point has this sort of special feature that it's right in the middle of our shape, and that's kind of why we're not doing the same thing for the green. Don't worry about that. Now, at this point, we're basically done. As amazing as it sounds, we're really actually at the foothills of understanding all of the symmetries of the triangle. I only have to say one more thing, which is let's think of the red line and the blue line as mirrors. Okay. Now, that might not sound very profound, but if you actually get a couple of mirrors, which have the same angles as these red and blue, and you look at what happens, you'll see that you get reflections of things in these mirrors, and basically mirrors reflecting in mirrors, and basically a reflection of a mirror in a mirror. We could call it a virtual mirror. So we could draw it as a line like that. And you can see that basically what we have here is a sort of kaleidoscope pattern. Okay, so if you put some shape in this chamber here, um, well, then you're going to have that shape's going to get reflected around these different mirrors. So it's going to have a reflection here. There's going to be another reflection up here. And basically, we're going to end up with 6 different images of our original objects. Now, why is that important? Well, how many symmetries are there of the triangle? There are 6. And those 6 symmetries exactly get and those 6 symmetries correspond exactly to these 6 chambers. And the way that these chambers change into one another via the reflections, basically the way that these chambers reflect in mirrors to form other chambers precisely corresponds to the sort of symmetries of our polytope, where we're doing some sort of transformation. Okay, so this is a part of this, which is this is the difficult bit, like to convey from a math educator point of view, because it's weird. It's like everything just appears at once at this point, and like it's almost a bit bewildering how much stuff you get out of this at once. So if you're just seeing this for the first time, like be patient and be willing to look at really simple stuff because it's like an explosion of possibilities right here. So okay, let's see this stuff actually happening now with GeoGebra because I think this is really going to help us. So we start off with our regular polytope, in this case a triangle. We pick any vertex O0, we pick an edge, link to it and call the center of that O1. We pick a face, link to that, call the center of that O2. We've got our special point, so 0, O1, O2. Now we're going to use those to form our kaleidoscope. So let's put this red mirror here opposite the red vertex. And let's put this blue mirror here opposite the blue vertex. So you can see that O0, O1, and O2 are forming this irregular triangle here. So this is a demonstration that I really love. I just think it's so geometric. So basically what I want to do now is to demonstrate that we're going to have the 6 different symmetries of the triangle emerging here from this kind of kaleidoscope with this red mirror and this blue mirror. And so this region here at the bottom left, we'll call this the fundamental region, and let's put something in there and see what images we get when we reflect it in these mirrors. So we'll start off with this little triangle here with a purple, orange, and black vertex. I'm just using those colors instead of numbers because it's easier to see. And now let's reflect this triangle in the red mirror. So we just do this with GeoGebra. So you can see that we've got another little triangle over here on the right. I won't bother drawing the edges, but what's basically happened here in this triangle on the right is that the orange and the purple vertices have been swapped over. Okay, so you can see that a certain kind of symmetry of the triangle has been enacted by reflecting in this red mirror. In a similar way, if we reflect this triangle in the blue mirror, we get this up here, where the black and the purple vertices have been swapped over. But we can go much further because actually the image of this blue mirror in the red mirror is going to form this other mirror that we could call a sort of virtual mirror. Well, let's give it a different color. And now we can also reflect things using that virtual mirror. Actually, if that makes you uncomfortable, we can generate everything just using the red and the blue. But the point is that using all these mirrors and using this kaleidoscope, we're going to end up with, in each of these 6 different chambers that we're dividing our triangle into, each of those is going to be occupied by a different sort of permuted image of our original 3 points. So let's just carry on, like reflect this thing that we just made in the red line, for example. Well, we get this shape up here at the far right, and we can ask, well, how does that differ from what we started with originally? And you can see that basically to get what we started with originally, where we've drawn the edges, if we get that triangle and then we rotate it by 60 degrees, we get this triangle up here. So this far right region that we've just made, this corresponds to a different kind of symmetry of a triangle, a rotation, as opposed to a reflection. Okay, so let's just carry on. What happens if we reflect this thing we've just made in the blue line? So we can do that. And now we can reflect this in the red line and we'll be finished. And so what I'm claiming here, is that we're getting all of the symmetries of the triangle, all emerging just because of how we started with that red and that blue line. And this is the fundamental idea behind Coxeter groups, because Coxeter groups tell us how we should place that red line and that blue line, as in what angle they should have between each other, etc. And you can tell that that's basically telling, and you can see that that's basically telling you how you should start off with your mirrors to make the right kind of kaleidoscope that's going to give rise to the symmetries of a triangle. And that's really the core of the whole thing. So let's unpack this a little bit now. Why don't we label these vertices 1, 2, and 3? And now we can see that basically this red mirror, we can think of this as a sort of symmetry operation, which is really swapping around vertices 1 and 2. So I normally like to just draw a little pictogram to represent what the symmetry is. You can see that this is swapping around 1 and 2. So we could also write this like this, that it's the permutation that swaps around 1 and 2. If you're not used to this kind of notation, don't worry, it's just for people that know. But basically, the idea is that we have these 3 numbers here representing our vertices, and then when we do this red symmetry here, we just swap around 1 and 2. So that's the kind of symmetry that gives rise to. Similarly, if instead, starting with this fundamental region here, we apply this blue symmetry, well, this blue symmetry here is going to be swapping around 2 and 3. So we could also call it the symmetry 2, 3. And you can see that basically it's going to leave 1 how it is, but swap around vertices 2 and 3. Okay, what about up here? This is really interesting because if you understand this case, you'll understand how all of these symmetries kind of can be composed together to yield the whole family of everything. So how do we get up here? Well, basically, if we apply the red symmetry here to this stuff, we get this stuff. So what we have here, we could say this is the result of doing this red symmetry after doing the blue symmetry. So we can write it like this. So what do I mean by this? Well, I mean that we start off with whatever we have, let's say in our fundamental region. So this picture really. And then we're going to apply this symmetry here. That gives us this picture here. And then we're going to apply this symmetry here. And that gives us this structure here. You can also work out what this composition is. Okay, let's do that. So basically, how do we do this? Well, we say, okay, we want to do this symmetry first, and then we want to do this one. So if we start off, let's say down here, well, when we apply the first symmetry, we're going to go up here. And then when we apply the second symmetry, this isn't going to change. And so the result, it turns out you can convince yourself of this. Well, let's do a bit more work. Okay, so let's say we start off down here. So we start off down here. So okay, so let's do the work. Okay, so let's say we start off now down here. So we start off here and we apply this symmetry first, and that doesn't change this. So then we end up here, but then we have to apply this symmetry. So that we end up here in the end. So we started off here, we end up here. So this point goes like that. And you can see that the net effect of doing this symmetry followed by this symmetry is this symmetry here, which rotates the triangle by a third of a turn. And so that's what we have here. And indeed, you can see, you can convince yourself now that we have all of the six symmetries of the triangle, and they're all emerging from just the basic symmetries. Okay, okay. So at this point, like depending on how much group theory you've done, you might be disappointed or you might be absolutely elated. It depends if you can understand how far this idea generalizes, because exactly the same idea basically applies to any regular polytope in any number of dimensions. And that's the really remarkable part of this. But I have a couple of other points to say. One of them is that you can probably see that, like, the really fundamental thing behind what's going on here is just going to be the angle between this red and blue line. That's the critical thing. If you actually try to make a kaleidoscope, for example, you get a couple of mirrors, you clip them together, you vary the angle, you'll see that it's all about that angle. And what is this angle here? Well, it is 60 degrees, or pi divided by 3 radians. Why is that significant? Well, basically because the Coxeter diagram, which corresponds to this, and this is going to sound a bit cryptic at this point because I'm not introducing things in, I'll introduce it methodically later, but the Coxeter diagram behind this situation looks like this. We have a red node and we have a blue node, and we link them by an edge, and we label that edge with the number 3. Why do we label it with a number 3? Because we're indicating that the angle between these things is pi divided by 3. If this was another number like p, then we'd be indicating that the angle in radians between these things is pi divided by p. In this case, p is 3. So that's basically the point. Like, I'm saying a lot of stuff at the end here, which isn't like I'm not defining everything rigorously yet, so that'll come later. But let me just give a flavor of where we're going to go with this, because this is really interesting. So if we go back to this GeoGebra program here, so if we go back to this GeoGebra program here, it has the nice feature that we can like play around with this original object here down in our fundamental bottom left region, and you can see that the sort of images of that stuff is going to change correspondingly. This is what you get in kaleidoscopes, and what makes them such a good toy. But here's something really interesting. Move this purple vertex, like ignore the other vertices, ignore the black and the orange ones if you can, and let's move this purple vertex towards O0. And notice what happens to the images of that purple vertex. Notice that as we move that purple vertex to O0, its images will go to the vertices of the triangle. Okay, so this is telling us something really profound and really kind of simple, but very profound, which is basically that if we imagine we started with like a dark room and all we had was this red edge and this blue edge, and these were mirrors in this dark room. Um, and now, if we pick where this vertex O0 is, and we look at the images of O0, imagine that we have like a little LED, a little purple LED that we sort of light up at O0 in this kaleidoscope, in this fun house of mirrors or whatever, and we look at the images of that LED. We look at where in this kaleidoscope, fun house, whatever, we see the images of this little LED. And the images of those are going to form the vertex set of our regular polytope. Okay, this is remarkable. This is basically the idea behind this so-called Wythoff or Wythoff construction. I never know how to say that guy's name, but basically that construction is basically just the idea that you get a kaleidoscope set up, so you get a mirror set up, and then you just look at the image of one particular point in that setup, and that gives you your polytope. So it's like instead of having your polytope with all of its vertices and edges and everything, we just kind of cut out a little symmetric region with the right kind of mirror setup, and that basically encodes all of the structure. And all of this setup works in higher dimensional space as well. And that's really the point of all this, actually. If this was only applying to the triangle, it would be a very limited interest, but it applies to all regular polytopes. So we can see this working with tetrahedra. We can see how it gives rise to things like. So we can see that this works with tetrahedra, cube. So you can see that this works with tetrahedra, cubes, the 120 cell. It's the same idea everywhere. So okay, we want to understand these Coxeter groups, and I've showed you this example here with a triangle. Now, I'm really claiming that most of the interesting things that go on in general are happening in this triangle, but we're going to have to look at some other cases to get more intuition. So the next case we're going to have a look at is the tetrahedron. And I think that when we have a close look at that, a lot of stuff's going to become clear. But just a couple of things to bear in mind here. The main thing is that we have this Coxeter diagram, which is telling us really that the angle between the blue and the red hyperplanes, if you like, or lines. The angle between them is pi divided by 3. And that's the essential information behind constructing this kaleidoscope. If you know that, and you know that you have this point O0 here on the blue line somewhere, away from the meeting point, then you can look at the image of that and you'll get your triangle. Okay, so this is this idea of this Wythoff. So this is this idea of this Wythoff construction. So it's basically the idea that if we move this purple point here towards the red vertex and we look at how everything's getting reflected around, we recover the vertex set of our triangle as that set of images. Now the way that we indicate this is we take our Coxeter diagram and then we draw a ring or a circle around this red node here. And that's just indicating that after we've got our basic setup like this, and that's just indicating that after we've got our basic setup like this, what we do is we look at the image of O0 under these different mirrors and reflections and things. So imagine that you have like a dark room with a red and a blue mirror, and then you light up this red LED over here. The images of that will give you all the vertices of your regular polytope. So that's all well and good, but let's move to a high dimensional setup so we can see the same idea working more generally. So the next thing we're going to look at is not the regular triangle, but the regular tetrahedron here. And we're going to proceed just as we did before. So now let's repeat what we just did, but for the tetrahedron here. So I'm going to describe again how we can find the symmetries now for the tetrahedron. I just love describing this setup so much because it applies to any regular polytope. It really feels like some kind of a magical formula to understand all of the symmetries, full stop. So we start with our regular polytope, our tetrahedron in this case. What do? First step, we pick a vertex. We call it O0. Then we pick any edge that's touching this vertex, and we call the middle of it O1. Then we pick any face that's touching this edge. We call the middle of it O2. We pick any three-dimensional cell touching this face, call the center of it O3. Okay, so that's it. We've run out of dimensions and we're done. Basically, we've got the building blocks now that we need to understand the symmetries of this regular tetrahedron. So it's just like before. Now we've got O0, O1, O2, O3. Those are going to form a irregular tetrahedron, and that's going to be like a little chamber of our big tetrahedra, and we're going to think of the walls of that chamber as being mirrored, and we're going to get a kaleidoscope thing going on. So let's see this more. Let's work this out more carefully. So firstly, we have these four vertices here: red, blue, green, and orange. Now let's take the red one, and we're going to form the sort of plane that corresponds to that red vertex. So what does that look like? Well, it's just the plane that goes through all the vertices except the red one. So it's the plane that goes through O1, O2, and O3. And you can see that that plane is going to be cutting through the middle of the tetrahedron. Well, it better do, because O3 is in the middle of the tetrahedron. And it's kind of cutting the tetrahedron in half. And I want you to think of this plane as a mirror or a symmetry operation. So if you reflect everything in this symmetry, you can see that the far left and the far right of the you can see that the far left and far right vertices of the tetrahedron are going to get swapped over. The other vertices are going to stay in place. So this is one of the fundamental symmetries of our tetrahedron. Now we just carry on. So what about for the blue point? Well, draw the blue plane through O0, O2, and O3, and then draw the green plane through O0, O1, and O3. So basically, so like the green plane goes through all the points except the green one, the red plane goes through all the points except the red one, and similarly so this is what we do. Now we've drawn all our planes and we're basically done. Okay. This is again I just love this part of the construction because it's like mostly with math constructions, you have to build something very precise and then you have to follow lots of very, very precise recipes and understand what's going on mathematically. But in this case, once you've drawn these planes, all you have to do is say, well, think of them as mirrors. And essentially, that finishes the job. Because if you imagine now that we have this red mirror, blue mirror, and green mirror, well, we can reflect stuff around in these mirrors. Indeed, like reflecting one mirror in another, or make like virtual mirrors like we saw before. So, like how we got this gray mirror as a sort of virtual mirror by reflecting the red in the blue for the case of the triangle. Well, we're going to have stuff analogous to that happening in this tetrahedral case, and that they're going to give rise to even more planes, just sort of virtual mirrors, if you like. And so in total, all these planes are going to cut up our tetrahedron into how many pieces? Maybe you want to pause the video and guess how many pieces we end up cutting the tetrahedron into. The answer is 24. Why 24? Well, because there are 24 symmetries of the tetrahedron. Okay, so 24 is 4 factorial. That's the number of ways that you can permute around 4 objects. It's the number of elements in the symmetric group S4. Because basically, if you have a tetrahedron, you've got 4 points, and any way that you can sort of relabel those 4 points is going to correspond to a symmetry of the tetrahedron. So if we number these vertices, 1, 2, 3, 4, for example, you can see that this red mirror here is swapping around vertices 1 and 2. That's one of the permutations, and that will end up labeling a chamber in the bottom right. So this is really a totally analogous situation to the one with the triangle here, where we're basically getting all of our symmetries from these basic, where we're basically building up all of our symmetries from these basic reflections. Okay, so hopefully I've conveyed some idea of what's going on, but I think it'll become more clear as we go through more examples. But let me just unpack how this geometry here ends up like being encoded in terms of Coxeter diagrams. So just like before, just like before, this Coxeter diagram here is really just telling us about the angles between these different mirrors, because that's the essential information that we need to understand the symmetries. So in particular, we know that we're working in a 3-dimensional case here because, so in particular, each of these 3 nodes here is going to correspond to one of the different hyperplanes that we have. Okay, so this is a little bit of a subtle point here. I always think it's best to think of the nodes or vertices of the Coxeter diagram as corresponding to the sort of hyperplanes that we're reflecting in. So, this would correspond to this red hyperplane here. But, in a sense, what we have here with these 4 points is a sort of irregular simplex, and this kind of plane that's red is equivalent information wise to the sort of vertex which is opposite it. So sometimes we want to be thinking about this as corresponding to this vertex. Sometimes we want to be thinking about this as corresponding to the plane opposite that vertex. We're trying to be a bit fluid about that, but we will be precise about what we mean. So I'm trying to tell you that this picture here, this Coxeter diagram, is telling us about the essential geometry happening in this picture on the left here. So each of these nodes here is corresponding to one of the different planes, and then the numbers are just telling us the angles between those different planes. So the angle between the red and the blue plane here is going to be pi divided by 3, or 60 degrees. And that's why we put a 3 there. So more generally, if we have a blue plane like this, and a red plane like this, and we look at the angle between them, and that angle is pi divided by p, well, we'd be indicating that by having a link between the red vertex and the blue vertex, which is labeled with a p. Okay, so this p here means the angle between these two is pi divided by p. So the angle between the red and the blue plane is pi divided by 3, or 60 degrees. Similarly, between the blue and the green plane, that angle is 60 degrees. Interesting question though, what's the angle between the red plane and the green plane? And it turns out that the answer there is 90 degrees. So 90 degrees is pi divided by 2, and that is, so 90 degrees is pi divided by 2, that's a right angle, okay? So this is really important, and this is a sort of subtlety about these Coxeter diagrams. So basically, when you have two mirrors that are perpendicular to each other, there's a sort of independence there in the way that those mirrors are acting. And it turns out that um, in terms of the Coxeter diagrams, where you're using these um, numbered edges basically to indicate angles, well, you, it turns out that there's a certain convention that you can use. So when you have a couple of mirrors which are perpendicular to each other, that implies that there's a certain sort of independence between those different symmetry operations. Okay, they're sort of working in a way where they're not interacting very much in some sense. And we have a sort of shorthand or graphical convention that kind of corresponds to this. And it's basically just that we just don't draw edges that should be labeled with a number two. Okay, so when you have a Coxeter diagram, it's going to have different vertices and different edges, and those edges should be numbered. Um, but when an edge should be given a number two, typically people just don't even draw it. Okay, so if you see a Coxeter diagram and it has a couple of vertices and there's no link drawn between them, that means that really there is a link, but that should be labeled with a two, and that means that these two hyperplanes are sort of perpendicular to each other. That implies a certain independence, and that independence basically is like justifies not drawing these edges in some sense, in some fuzzy sense that you don't need to understand at the moment. So just know that we don't bother drawing edges that should be labeled with a number two. Also, when a edge should be labeled with a number three, sometimes we don't draw that number three. This is just because threes appear so much in Coxeter diagrams that there's just like a shorthand where we just don't bother writing a three. Okay, so if you see this picture here, you now know how to unpack it properly. Firstly, you say, okay, those are edges without numbers, so let's put threes on them, and then let's add in this missing two here. And now this is telling you all the angles, and this is basically telling you how to cook up this setup. And now finally, if we take this Coxeter diagram and we circle this vertex here, what do we have? Well, this is describing this Wythoff construction again. Well, this is describing this Wythoff construction again. So this is telling us, well, start off with this mirror setup and then look at the image of O0 within this kaleidoscope here, and that's going to give you your whole vertex set of your tetrahedron. And so you might see people write things like this, that this is equal to the tetrahedron. Now, this is really fascinating, okay? This is really the essence of what I want to talk about today is how you can go from a Coxeter diagram to a regular polytope. So, and it's really an amazing thing to study for all sorts of reasons. So we can look at this from a sort of combinatorial or topological viewpoint, where we can see how our polytope comes about just as a sort of combinatorial structure, where we know which faces are touching which vertices, blah, 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 but we don't really know about the spatial layout. But we can also look at this question in terms of actual coordinates, and we can get representations, and we can get the actual geometric structure with coordinates and things arising straight from the Coxeter diagrams. That's the most I find that the most fascinating part of this. But also, we can vary things. Okay, so we can take this Coxeter group, and then we can say, well, what if we ring the blue vertex now instead of the red vertex? So what does that mean? Well, what that means is we take this setup here, but then we're interested in the images of O1 here. And it turns out that those are going to end up appearing on the middle of every edge. And if we join them together, we end up getting a octahedron. Okay, so you could say that the octahedron is the truncation or rectification of the tetrahedron. I'll just say that for the geometers out there. But the amazing thing is that this is emerging from our Wythoff construction all at the same time. And maybe at the point where we're looking at tetrahedra, this isn't interesting enough for you, but believe me, when we are able to do the same idea in higher dimensions, and we can look at things like, for example, the four-dimensional simplex, and how we can look at the rectification of that and get other shapes, or you know, it's the generality of this, and it's the unity of it that makes this so worth studying. Okay, so one of the main things that I want to convey is how we can go from a Coxeter diagram with a ringed vertex back to the regular polytope. Okay, so basically, if we have a regular polytope, for example, this triangle here, well, it turns out that there's a certain Coxeter diagram that we can draw. Actually, it's this one. And then we ring one of the vertices, and then this means the same thing as our original triangle. So what we want to understand is how we can go from here to here. So basically what this means. Or more generally, if someone draws a more general kind of Coxeter diagram, how can we look at that and figure out which regular polytope that corresponds to? It turns out in this case, this corresponds to the 16 cell. But how can we figure that kind of stuff out in general? That's really what I want to talk about here. Now, it's a challenging thing to discuss because we're going to be using a bit of group theory, but honestly, the rules themselves are pretty simple. It's just that it's a bit alien the way that we sort of interface with these diagrams. But it all makes sense if you look at it in terms of mirrors. That's really the point. So let's go back to our original thinking about the triangle and how we can get the Coxeter diagram for that. And if we view things this way, what it's going to basically allow us to do is to see the connection between here and here. So remember how we do this. How do we find the symmetries of our triangle? We pick any vertex and call it O0. We pick any edge touching that, call the center of that O1. We pick any face touching that edge, call the center of that O2. And it would carry on in a similar way if we're working in a higher dimensional case. But let's just focus on this triangle. So we could think of these vertices as labeled 1, 2, 3. And then this, we could call it 1, 2. The permutation swapping around 1 and 2. We could also, which I prefer, draw a diagram of it like this. It swaps around 1 and 2. Similarly, W1, we could say it swapping around 2 and 3, or we could draw it as a diagram like this. So the Coxeter diagram for the triangle, we don't really have to label or color the vertices, but I like to. But we should draw an edge. We'll put a 3 on it. But also I'd like to call this W0, and I'll call this W1, and we circle this. Now, when we circle it, you should not think of W0, but the vertex opposite it, which is O0. That's the vertex that is like our LED that we're putting in this kaleidoscope, which has these as mirrors. And when we reflect it round, we get the vertex set of the triangle. So that's the main connection here. And the sense in which this tells us the structure of the triangle is that this number here is telling us the angle between the blue plane and the red plane. It's telling us that that's pi divided by 3. If this was a p, then this would be pi divided by p. So, so the number on the edge is telling you the dihedral. Well, if the number on the edge is q, that means the dihedral angle between those corresponding hyperplanes is pi divided by q, if that number is q. Um, so also this picture here is intimately related to the symmetries of the triangle. So we can see this by these little pictograms here. But I'd like to draw some other way of picturing this. So this is our fundamental region. This corresponds to the identity. So we could just draw a triangle here. Now, this here corresponds to this permutation where we swap around 1 and 2. You can see that in several different ways. You can see it by, if you think about these colors here as 1, 2, and 3 in this little pictogram, you can see that in the result, those numbers have literally been swapped around. So that's a very cute way to see it. But you could also say that we're applying this symmetry operation to the identity, and this is this. That's why we get it here. Similarly, this is permuting 2 and 3. Now, a really good question here is what should we draw here? Okay, because if we understand this, then we'll understand the central connection here with the group theory. Okay, so what do we put here? Well, in a sense, we can just let the kaleidoscope do the work for us, okay, because we can already see the answer here. But what kind of permutation is it? How can we understand it? Well, in a sense, what we're doing is we're reflecting this in this red mirror, and that's going to give us whatever is here. So whatever is here should be the result of doing this 1-2 permutation, which corresponds to using the red mirror, after whatever is here, which is this. And how do we compute this? Well, it says first do this operation, then do this operation. So if we start with a point, let's say this one here, well, first we go up here, then we apply this operation, which does nothing. So it turns out that if we start up here, we go here. And similarly, you can calculate that this is going to be a rotation, sending 1 to 2, 2 to 3, and 3 to 1. And you can similarly compute the other two of these symmetries. Now, the really interesting thing here, and this is so deep, is that what we actually have here is this group S3. So this is the symmetric group on 3 elements. In other words, if you take 3 things and you put them in a row, like 1, 2, and 3, and then you think about all the different ways that you can swap stuff around. So maybe you swap around 1 and 2, or you could rotate things around, or you could do all sorts of things. Well, there's going to be 6 different possible permutations, and the way that you compose those with each other is this symmetric group S3. And so what we're seeing here is that this group is generated by W1 and W0 here. So, given all that, what have we learned, and how can this be applied to our basic question? Okay, so what's our basic question is how can we go from this picture here to this picture here? Okay, so what's going on with all this group theory? Okay, right. So what is a group for a start? Maybe that's a good place to start. So a group G, it has a set of elements, and then if you have any G and G dash, which are elements, then we're going to have another element which we could call G after G dash. So we have some notion of being able to sort of take two elements and multiply them in air quotes and get another element of our group. So we know about groups, like we've just seen a group here. Um, this is this group of permutations of three things. Now, there's interesting stuff going on here already. One of them is that we have group structure here, but we're also associating it with spatial structure. So this has to do with what are called group representations. So we're going to get back to that later. But for now, I really want to just look at this in terms of the group theory. A subgroup, let's say S, would just be a group that's contained in another group. So for example, we have this group of these six different permutations here, but we also have this subgroup here. So this is a subgroup of, well, I'll call it S3, okay? So S3 here is this whole thing. Let's call this S3. So here I'm talking about this symmetric group with three elements here. So this is a subgroup. Why is it a subgroup? Well, yeah, we have, so I say that this is a subgroup of S3. So why is it a subgroup? Well, it has a feature that if you multiply elements within this subgroup by each other, you get something else that's in this subgroup, right? So if you do this reflection after this reflection, that just gives the identity because it's like reflecting in this twice does nothing. And here's the other idea that we're going to need, and this is very interesting. Let's suppose we have some element G in, let's suppose we have some element little g of our group, right? So I should just say notation. This means contained in, and this means is an element of. I just wanted to explain what this notation meant. Anyway, this final definition, if we have an element little g and we also have our subgroup S, then what we call the left coset, which is something that we write like this, is defined as follows. It's G after H, where H is an element of this subgroup. All right, so the idea here, let's say we have some subgroup, so S, so maybe this is, maybe it has two elements, S1 and S2. And then we also have G, which is something in our group. Well, then we can talk about this left coset here, GS, and this is a set, might not necessarily be anything more than a set, but it's a set. And the way that we get it is like this. So we do G on little S1 and we do G on little S2. And when I say we do G on it, I mean we're doing group multiplication here. So notice that like these two could end up being the same thing. So this might end up being a set with one element. It's possible that things can collapse on top of each other. And so really we're just sort of tracking what happens when we do G on each of these things. And we're going to see that there are very profound geometric ways to interpret this in our context. So this is this idea of a left coset. That's all the group theory we're going to need. Now let's do this. So we have our regular triangle here. And as I've been trying to convey, we have our regular triangle here. And as I've been trying to convey, we can think of this as corresponding to this Coxeter diagram here with this ringed vertex here. Now, I would like to, I would like to also name these vertices. I'll call that one W0, and I'll call this vertex W1. So, what does this picture mean? This is really the core of what I want to talk about. Basically, what it means is that we can consider the Coxeter group generated by W0 and W1. Now, we can think of this actually as something abstract. So this is a little bit beyond what I wanted to get into, but since we're here, the idea is basically that each of these corresponds to a sort of symmetry reflecting in a hyperplane. And so we know, for example, that if we do W0 twice, that's going to give the identity. So that's one equation that we know holds. What else do we know holds? Well, it turns out that if you do, let's say, W0 after W1, well, then what you're basically doing is you've got these two sort of hyperplanes which have a certain angle between them. Um, let's say the Coxeter diagram looks like this. So you know that this angle here is pi divided by p. So let me try and give a bit more intuition here, right? So let's suppose that we have two vertices in our Coxeter diagram, W0 and W1. Now these are going to correspond to hyperplanes. And then consider this kind of expression here. It means first do W1, then do W0. So first we do W1. Let's say we start off with our point over here. First we reflect it in this hyperplane here. We get over here. Then we do W0. So we should have a little after there, I guess. And then we end up over here. So what's the net effect? Well, the net effect is a rotation by 2 pi over p. It just happens that reflections work that way when we compose them. So what that means is that if we do this operation p times, in other words, if we consider this, then we end up getting the identity. And in this kind of way, um, you can think of a Coxeter group as something which is defined completely abstractly. So yeah, you could say these things correspond to um, symmetries and etc. Or you can take a more kind of group theory point of view where you say um, these are just generators and they have these equations that they satisfy because they are reflections. Anyway, you can think of this as a group. Now, there's another way that you can get at this group, which I think is even nicer, which is basically um, you can you can actually associate these things with sort of transformations of actual space. Okay, so in these little pictures, I've been drawing these triangles, and you can imagine these are drawn in the plane, and there's an actual transformation from the plane to itself, basically a 2 by 2 matrix, which corresponds to applying this symmetry. And then you can do matrix multiplication, which is going to do what the group theory is doing, but it's spatially realized, and that's even nicer because it sort of fleshes out the story. So we're going to talk about that later, but for now, I just want to look at this situation in terms of these Coxeter diagrams because, yeah. Um, so the first thing to look at, and this is an interesting kind of thing to think about, is what does this diagram mean here? I'm going to draw a green box around it just to show you what I'm talking about. So what does this mean? Well, um, if we interpret this diagram here to mean the group, let's interpret it as follows. Let's call it the subgroup of S3 generated by one, two, and two, three here. Okay. Well, that is S3. So this is S3. We get every element like that. We've shown that here, right? We've shown that by multiplying together these basic things in different ways, we can get everything in S3. So this is the whole, so this picture here means the whole of S3. What does this mean? Well, this means the subgroup of S3 generated by just W1. So what's that mean? Well, it means that we can get W1, we can get the identity, and we can take stuff and multiply it by other stuff in this set. And everything that we get forms this subgroup. Well, it turns out that that is everything we get, because doing this reflection twice gives an identity. So this is, itself is this subgroup. So what does that mean? Well, we have all of these different permutations of the triangle, but now we're just talking about this kind of subgroup where we're just either flipping the triangle over like that or leaving it alone. What does that have to do with anything? Well, here's a really interesting question to ask. What are all of the symmetries of the triangle that leave O0 invariant? What kind of operations can we do that aren't going to move O0? Well, we could do nothing. That would be this. The other option would be that we swap around 2 and 3, but we're still leaving 1 in the same place. Okay, so in fact, this is the subgroup leaving O0 invariant. And the punchline is that we really want to think of this as corresponding to O0, corresponding to vertex number 1. Now that, what I just said is a bit weird, and I'll have to do some work to try and make that more formal. But basically the idea is that if we want to refer to a particular vertex, we think about all of the symmetries that leave that vertex alone, and those correspond with that vertex in some sense. I'm going to make this more precise as we go on, but let me continue with this. So what I really want to do is explain how we can get the triangle starting from this picture here. Let's take a look at this diagram and let's ask what kind of subgraphs this thing has which contain this ringed vertex here. So one answer is this. And I'm just going to tell you that this corresponds to an edge. Well, that's going to seem a bit mysterious at the moment. Hopefully, I can explain why that's the case later. But let's think about this more in the fashion that we were just thinking about this. So we can forget about this ring. This is a reoccurring theme that when we're thinking about the group theory, we don't need to worry about which vertices are ringed. So we call this W1, and this is going to be the subgroup of S3 generated by W0. So if we take a look at our diagram, we can see it's either going to be the identity or this swap 1, 2. So, okay, how does that help us? So what this means, this W0, it means this subgroup here. This is a subgroup of S3. All right, but what's it really telling us? Well, what it's really telling us is that these two operations here are the things that are leaving O1 fixed. We can see that this is going to be leaving O1 fixed because it's a hyperplane that goes through O1. If you reflect a point that's inside a hyperplane, that point isn't going to move. But another way we can think of this is if we think about the triangle with vertices 1, 2, and 3, we can think about this as a sort of edge, let's call it E, and this set of symmetries here is the set of symmetries that leaves E invariant. So we can start to build up some really powerful ideas here now. So let's draw this picture again because it's worth doing this properly. So let's call this O0. I'm also going to call it V. This is O1. W0. And this is W1. Now what we saw, and so remember W0 is this reflection 1, 2, and W1 is this reflection 2, 3. Now what we saw is that the symmetries that leave this V vertex here fixed are going to be either the identity or this W1 symmetry here, right? So we have all of these 6 different symmetries. I won't bother writing them all out again, but out of all of those, the only ones that leave this vertex here alone are the one that does nothing and the one that just sort of reflects over here. Similarly, let's call this E. All right, so we could also number these vertices. So E is like the edge through 1 and 2, if you like. But again, we can ask, what are the symmetries that leave this edge E alone? And really, this edge E corresponds with this O1 here. So as long as, we know that W0 is going to leave that alone. So this is really going to be the subgroup of S3, which is generated by W0 here. So in other words, if we do an identity or this permutation where we swap round 1 and 2, that's leaving this edge invariant. Okay, fair enough. How does this help us? Well, what about if we want to get the other vertices? Well, what we could do, oh, by the way, we could also write this. So remember, let's draw this in terms of Coxeter diagrams now. So for the entire triangle, it has a Coxeter diagram like this. So incidentally, this is the Coxeter diagram for the whole thing. And then this little diagram here corresponds to this, and this little diagram here corresponds to this, because I'm just sort of telling you which generators or fundamental symmetries we're using to make these groups. Anyway, the point here is that, yes, this is a vertex, but if we then apply a particular symmetry to this vertex, like let's like for example, we could apply W1 to the vertex V. Well, in that case, what we're really doing here is we're computing this left coset here, because remember this V is really corresponding to this subgroup here, which you know, vertex V is invariant under. And then we're going to multiply on the left by this symmetry. And basically what we're doing here is essentially finding the form that we get when we apply this symmetry to our vertex V. So we can see that this is going to correspond to either this or, let's see, so we start here, we go here. Right, so now we get this as our result, and this is the name of this vertex here. Why? Because we can get this vertex here by starting with V and then either performing this symmetry here where we're reflecting in this, or this symmetry here where we're sort of rotating everything round. And in a similar way, if we apply this symmetry here, which is this. If we apply that to V, then we get this vertex up here. And similarly, like what would we call this edge here? Well, we could call this edge here the result of applying this symmetry here to our original edge. And then we can write this out, okay? So this is just another left coset. So forgive me for being messy, but um, we're applying this symmetry here to this subgroup here, and then we just multiply this out. So that's that times that, and then that times that means this. And if we do this first and then the other, so we get this. And that should be corresponding to this edge here, because we can get this edge here by taking this edge here and applying this symmetry. Or, if we take this edge here and we apply this symmetry here, well, that's again going to result in this. Okay, so far, what we've basically been doing is understanding the meaning of this, which is a triangle. Now, the next big goal that I'd like to approach is to understand that this is a tetrahedron. So a triangle is a two-dimensional simplex. Tetrahedron is a three-dimensional simplex. So I'd like to understand this, and I'd like us to understand better the combinatorics that are going on here, because it's absolutely fascinating. I think that this is a nice time to make a little bit of a remark, and I think it's a bit funny. So you know, I sometimes wonder um what I must look like to people who don't know about maths, and they look at the kind of stuff I'm writing and they wonder at what I'm thinking about. So, you know, imagine someone who doesn't know any maths and they look over your shoulder and you're writing things like, you know, this equals 9 over pi plus y or whatever. So that looks like complicated maths. Um, if you look at someone's shoulder and they're writing things like, for all x in n, there exists an arrow from A to B called G, that looks kind of complicated as well. Now, if you look at over someone's shoulder and they're drawing things like this, now what's going on, right? Um, Maybe they're drawing these string diagrams and they're sort of like, oh, well, this equals this. And I find this really kind of funny because this is like the sort of language of string diagrams for monoidal categories, and it's extremely sophisticated and it's just going with the flow of the mathematical structure completely. So if you look at things like graphical linear algebra or, Bob Koech's book, Picturing Quantum Processes, these kind of approaches to things, or, Penrose string diagrams, Feynman diagrams, all of these kind of string diagram or wiring diagram kind of pictures that are being used in applied category theory now, they are profound, but they also look so simple, right? So there's some kind of weird thing going on where mathematicians are sort of getting out of this hole that linear text puts us in my opinion. I think that the typewriter did a lot of damage to mathematics in some ways, which I think is now being undone thanks to, higher dimensional mediums of communication and things. But, these string diagrams are one thing, but then when we get to these Coxeter diagrams, which, are something really quite different, but this this thing about language, I find it quite hilarious because now you have people like there's a profound video by Norman Wildberger where he talks about how you can get at this Gelman theory of quarks by considering this Coxeter diagram here. You know, the triangle, basically, if you like. If we drew this, it would be the triangle. But, you know, it's kind of hilarious that you can end up thinking about this and we, you know, after all our work, we can finally understand what is the meaning of this. And someone would look over your shoulder and they'd be like, okay, yeah, that doesn't look very complicated. But in a sense, that's really good because it means that we're interfacing with something which, even though it might not be intuitive, it is simple, like in terms of information and so on. Anyway, we'll see more about this later. I just thought that's a bit of a tangent. But yes, what we want to understand now is this. Remember, when we don't number the edges, we can put number threes on them. That's what that means. So we already know because of Schlafly symbols and so on that this is the tetrahedron, right? But how could we actually compute this? So here's basically the idea. So we can take a look at our tetrahedron, remember how we constructed this thing, and remember that we have these mirrors. So let's number these vertices like so. And now we can see which kind of symmetries these different mirror things correspond to. So this reflection in this red plane here, that's going to swap around 1 and 2. But it's going to leave 3 and 4 where they are. So that's going to be the effect of reflecting in W0, W0 being the hyperplane which is opposite O0. So let's remember the setup here. We have our tetrahedron with its vertices, which we're going to number 1, 2, 3, 4. And then recall how we got these special points. We picked a vertex O0, picked an edge next to it, and a center of that is called O1. And O2 is the center of the face touching that. And O3 is the center of the whole thing. And then W0, let that be the plane which goes through all the O points except O0. And similarly, this is W1. It's the plane that goes through O0, O2, and O3, and so on. Yeah, we also have the green plane, which is W2. That's the plane that goes through O0, O1, and O3. So we have these three different planes, and they're the fundamental symmetries of the tetrahedron. And we can see the effects that reflecting in those planes have, how they permute the vertices of the tetrahedron. And this is describing how this Coxeter group, that should be a W1 there, how this Coxeter group works, okay? So here's the idea. What we're trying to convey is that this diagram here corresponds to the tetrahedron. And so we're going back to our old 3D picture of our tetrahedron. So we really want to show how we go from this picture at the top right to the tetrahedron, but of course we're going to start by looking at everything. So let's actually start with our tetrahedron with vertices numbered 1, 2, 3, and 4. Let me just clean that up a bit. So now let's remember how we got this picture. So we got this picture by taking our tetrahedron and then we're basically adding some planes. And we're thinking of those planes as these symmetries, which are making this Coxeter group. But how do we get that? How do we actually build this? Well, we start with any vertex. We call it O0. We pick an edge touching that. We call the center of that O1. We pick a face touching that. We call the center of that O2. And then we call the center of the whole thing O3. And then we let W0 be the plane that goes through each of these O points except O0. So W0 is the plane that goes through the points O1, O2, O3. And similarly, W1, the blue plane, is the plane that goes through all the points apart from the blue point. So it's the plane that goes through O0, O2, O3. Remember, 3 points define a plane if they're three non-collinear points in 3D space. So yeah, that's how we get these planes. And then the idea is we think of those as symmetries. And composing those symmetries gives us all of the symmetries of the tetrahedron. So for example, this red plane here, if we're reflecting that, well, it's going to swap round vertices 1 and 2. It'll leave vertices 3 and 4 where they are because they're actually contained within that plane. And so we can think of W0 as corresponding to this permutation here. If you want to think of it as a function, it sends 1, 2, 3, 4 to 1, 2, 3, 4. So it sort of swaps around 1 and 2 and leaves 3 and 4 in the same place. So that would be like the function W0. And similarly, you can see what W1 is doing here. So what's W1 doing? Well, I think it leaves 1 and 4 fixed and it swaps around 2 and 3. That's what W1 is going to do. But then on the other hand, this final plane, W2, that's going to swap around 3 and 4 and leave these two fixed. That's going to be the effect of W2. So really, we can think of W0, W1, and W2 as members of the group S4, which is the group of permutations of the set of four elements. So, okay, how does that help us? Well, basically, now we have a sort of interpretation of this diagram. Actually, let's draw this diagram. Okay. I'll just ring that vertex. Don't worry about what that means for the time being. Now, what we can do is say, okay, what about if we consider a subgraph of this or a subdiagram? So we take this and let's delete this stuff here. So what would this mean? Well, okay, let's forget about the rings again. Well, we can think of this on the left as a subgroup of this thing on the right. So it's the subgroup generated by W0 and W1. So what does that mean? Well, what it means is basically, what if we can only use the red mirror and the blue mirror? That's basically what this means. So what if we can't use the green mirror? Okay, so we think about all the symmetries we can form, all the permutations of this set of four elements, but we're not allowed to use the green mirror at all. So we can only use the red mirror and the blue mirror. Well, in that case, if you think about it, the only place where interesting stuff is happening is on this sort of front face here of this tetrahedron. Effectively, we are working with a triangle with respect to the symmetries, right? How many symmetries can we build just using W0 and W1? In other words, only being allowed to reflect in the red plane or the blue plane. Well, in that case, there's only 6 things we can get, and they correspond to the 6 different chambers that the triangle would get sliced up into. And also, and this is the punchline, this is the triangle, and this is the tetrahedron. And so this is our first lesson. When we have a Coxeter diagram with a ringed vertex, and we take a subgraph of that, a connected subgraph that contains that ringed vertex, that is the Coxeter diagram describing that kind of cell with the appropriate dimension corresponding to the number of vertices we have. So we're going to see this much more clearly in a minute. Hmm. Yes, I think so. I think, in fact, this is the right time to have a bit of a um to look at something a bit different. Yeah, I'm going to go through this calculation. Um, so let's just remember where we are. So I'm trying to give a flavor basically of how the tetrahedron corresponds to this sort of picture. And what we've just been looking at is this interesting notion that the tetrahedron has triangles as faces and that this is a subdiagram of this. Well, in terms of Schlafly symbols, this is not so surprising, right? I mean, for example, if we have a four-dimensional regular polytope, PQR, we can write it like this. And if we look at this, well, that's PQ, and that's telling us the shape of the three-dimensional cells within this four-dimensional polytope. So, for example, if we have the hypercube, well, how can we think about this? Can we think about this now in terms of Coxeter diagrams? Yeah, sure we can. So what happens? Well, we have these points, O0, that's going to be a vertex of our hypercube. O1, that's going to be the center of an edge touching that vertex. O2, that's going to be the center of a square touching that edge. O3, that's going to be the center of a cube touching that square. And O4, that's going to be the center of the whole thing. Now, W0 is going to be the affine hull of all of the O points except O0. So that's going to be a three-dimensional flat within four-dimensional space. It's a three-dimensional hyperplane. Similarly, W1 is, the same kind of thing, but it has everything W apart from O1 in it, and so on. And so we can then think of these as corresponding to W0, W1, W2, and W3. And basically, WI is like the hyperplane opposite OI in this simplex, this sort of irregular simplex that's formed by these vertices. And then these are telling us the angles. So here we have this 3D hyperplane W0, and here's another one, W1. And this is telling us that the angle between these, the dihedral angle, is pi divided by 4. And so these numbers here are just telling us the angles, basically, in terms of geometry. But in terms of figuring out the actual structure of this using group theory, it's much simpler. Okay, so basically, we have four-dimensional space, if you like. I mean, this is a nice geometric way to think of it. Each of these hyperplanes is basically going to give you a sort of reflection from 4D space to 4D space, and that's going to enact a certain permutation on the set of vertices um, of our tesseract. And so we could, figure out exactly how all this works, but it takes a while. So let's just draw a rough picture and move quickly. So we have these different primitive reflections and we can build them all up. But what we can also do is get at the sort of substructure of this tesseract just by using this diagram here. So here's how we do it. Firstly, by inspecting these numbers, we can understand the angles between these hyperplanes, and we can assure ourselves that this is what we could call a spherical honeycomb, in the sense that we're filling space, but we're filling this sort of spherically curved space. In other words, it's a regular polytope. And given that we have a certain way of proceeding, we count how many nodes there are, and that tells us the number of dimensions of space that we're working in. So this tells us we're working in four-dimensional space. Now, the next thing that we do is we note that each of these nodes is going to correspond. So let's say n is 4. Okay, n is the number of dimensions that we're working in, the number of nodes that we have. So then each node corresponds to a n minus 1 dimensional hyperplane. Okay, and then when we have a pair of nodes, W0 and W1, say, we look at the edge that's connecting them and we look at the number on the edge. And if that number is P, then it means that the angle between W0 and W1 is pi divided by P. That's how we read the numbers. What about if we pick a node W0 and another node W2 and they're not linked? What's the angle then? Well, remember the secret convention that when nodes are not linked, they really are linked, and we should put a number 2 there. So if we're going to draw this all out properly, we've got to make sure things are linked up in the correct way. But we don't bother drawing those links with 2s on just by convention. But you can follow all the math just the same if the angle is pi divided by 2 instead of pi divided by 4, whatever. But anyway, let me just tell you how to proceed. I've been trying to explain this stuff step by step, but I think we just have to sort of dive in at some point. So let me just do this and then we'll talk about it afterwards. So we have this structure. Let's say someone hands you this and you're really into Coxeter diagrams, but you've never seen a tesseract before. You don't know what kind of shape it has. So what do you do? Well, firstly, you count how many nodes there are. You say, okay, there's 4. The number of nodes, n, is 4. That means we're working in 4D space. Cool. Okay. So we expect that this is going to be a regular polytope. Well, let's just say it's going to be so we expect this is going to be a polytope. So it's going to have 3 cells, faces, edges, and vertices. So we want to find out what these are and how they are touching each other so that we know the whole structure. Okay. So firstly, what are the 3 cells? Well, let's ask a question. So here's the key thing that we have to do. I'm not going to justify this yet, but the first thing we want to do, we have this. Okay, we're given this diagram, and we want to find out what kind of polytope this corresponds to. So the first thing we want to do is figure out what shape the 3 cells have. Okay, there are these 3-dimensional cells. What kind of shape do they have? So here's what we do. We find the size 3 connected subgraphs that hold the ringed vertex. So what on earth do I mean by that? Well, a subgraph is just a graph contained within a graph. So if you take any graph, for example, this one, and you pick some of the vertices, say those three, then you can draw the subgraph on those. That just means you draw the vertices that you have in that and you connect any two vertices that are linked in the original graph. So we're looking for the subgraphs of this that have three vertices and they contain this ringed vertex. Well, in this case, there's only one. So what this tells us is that this is the only, and so what this tells us is that this corresponds to the only kind of three cell that we have. And what is this? You may recognize it. It's the cube. It's 4,3. So this is telling us something, okay? But in fact, this works more generally. So what about if we want to find out k-dimensional? So if we wanted to find out the k-dimensional cells of our polytope, we can look at the size k connected subgraphs holding the ringed vertex. So we can carry on, okay? So if we do something similar to this, but we instead use a number 2 here, well, then we end up getting this, which describes the structure of the faces of our tesseracts, that they are squares. Now, it's much deeper than this. We're not only getting all of the different shapes of the cells, we can get all of the structure by digging into these Coxeter diagrams, but it takes some describing things verbally in some sense. It's difficult to explain. I think the I think maybe the best thing for me to do is to go through a calculation, and I'll explain roughly what's going on, and then I think I'm going to have to come back to this because yeah, the issue with these Coxeter diagrams, it's not that they are particularly complicated. It's more that there's so many things going on at once. It's so much easier to understand them through examples than it is to understand them, um, you know, in terms of theory, although it's all possible. So let's have a look at the 5 cell. So what is the 5 cell? Well, I'll draw it for a start. It's basically a four-dimensional version of a tetrahedron. So we have 5 points and they're all linked to each other in 4D space. Okay, here's the Coxeter diagram. There it is. So let's draw this nicely. Here's our 5 cell. And here's the corresponding Coxeter diagram. I'm not going to bother labeling these edges with threes. So here it is. Now we want to understand this thing. So the first thing that we want to do is to understand how many dimensions we're working in. So we count how many nodes there are. There are 4. That means we're working in 4 dimensions. Okay. So the next thing is, what do the 3 cells look like? Well, they're going to look like the size 3 subgraphs of this that have the ringed vertex in them. So there's only one. And it looks like this. And we recognize this as corresponding to the tetrahedron. Turns out, let's say we have n nodes all in a chain like this. We call that AN. Now, the number of elements is going to be n plus 1 factorial. So 5 factorial is 1 times 2 times 3 times 4 times 5. So what this means is that when we have this is your n-dimensional simplex that has n plus 1 vertices in n-dimensional space. And the number of symmetries that has is the number of permutations of n plus 1 elements, which is n plus 1 factorial. This is the number of elements in the symmetric group. So now, how many tetrahedra do we have in this 5 cell here? Well, this 5 cell is the hang on. Maybe I should have said anyway. Yeah, maybe I should have said Sn plus 1. Anyway, so this 5 cell has generators W0, W1, W2, W3. So we're talking about the 5 cell, we're talking about permutations of 5 elements. So we're talking about S5 in this case, basically, the symmetric group. And we know the number of elements it has is going to be 5 factorial. And then what we're talking about here is the subgroup of S5, which is generated by W0, W1, and W2. They're going to be certain reflections. So we have five factorial elements in our group to start with, but then we have this subgroup with 4 factorial elements. That's the subgroup generated by these guys. And so the number of left cosets is going to be 5. And each of those left cosets is going to correspond to one of the tetrahedra, which is inside this 5 cell. That tells us about the number of tetrahedra. Let's carry on. So firstly, we were interested in size 3 connected subgraphs holding the ringed vertex because we wanted to find out about the 3 cells. Now let's look at the size 2 ones. So we have this. So we can draw that. Let's draw it. Well, fair enough. Now let's ask something. I'm not really going to justify this, but let's just ask if we wanted to get this. We wanted to get this subgraph out of this. We wanted to take this and delete the minimum number of vertices possible so that this ends up being the connected component holding the ringed vertex. Well, what's the least work we can do? Well, the least work we can do is just delete this guy. If we delete that, then that's all we have to do. And then the part holding the ringed vertex, the connected component, is going to look like the form we want. So let's just do that. We just want to delete the minimum number of vertices possible so that we end up getting the connected component around the ringed vertex of the appropriate size. So let's consider this Coxeter diagram. And now we can ask, what shape does this correspond to? So to determine what shape this corresponds to, we just look at the connected component holding the ringed vertex, and we know what that corresponds to. It corresponds to a triangle. Okay, so this gives us our second shape. It's a triangle. Now, how many of these are there in our 5 cell? Well, our 5 cell has 5 factorial elements in its group of symmetries. And then what we're looking at now is the subgroup of S5 generated by these elements here. So how many elements are there in this subgroup? Well, it turns out that the way we calculate this is we look at the different connected components and we multiply the number of elements in the subgroups corresponding to those with each other. And when we have two dots, that's a 3 factorial. When we have one dot, that's a 2 factorial. So this is counting this. And how many is this? It's 5 times 4. Divided by 2, it's 10. So again, what we can do is we can think about this as a subgroup of S5 generated by W0, W1, and W3. And then each of these actual triangles is going to correspond to a sort of left coset of that. So imagine we have our um, so imagine we have our four-dimensional simplex, and then we look at all of the symmetries of that that leave this sort of fundamental triangle, the one with O2 in the middle of it, it leaves that invariant. And that subgroup is going to be the subgroup generated by these guys. And then when we look at the left cosets of those, and this is how many of those there'll be, they correspond to the different actual triangles of the simplex. But it's easier to think about combinatorially, of course. We just think about, well, we have 5 vertices, we need to select 3 of them, 5, choose 3, and that's all we need. But, you know, that's the point is that this Coxeter view works much more generally, much more generally. So it's interesting to view it in both ways. Let's carry on anyway. So the next question is, how many edges do we have? So an edge just corresponds to a single dot. So we just want to get this Coxeter diagram here. So we ask what's the minimum amount of damage we have to do to the original structure to get the connected component with the ring vertex to look like that. Well, we just have to delete W1. This gives us an edge. And how many of these will there be? Well, it'll be 5 factorial divided by 2 factorial, 3 factorial. It's 10 again. And then finally, for the vertices, okay, so for the vertices, we actually delete the ringed vertex itself. So our Coxeter diagram looks like this. If you like, we're actually interested in the connected component which has the ringed vertex, but that is non-existent, as it should be, because we're corresponding to the zero-dimensional thing, which is a vertex. And the fact that this is floating around just corresponds to this convention that we only do the minimum amount of damage we have to. It's a bit cryptic, but let me just show you the calculation. So how many vertices will there be? Well, it's just this divided by this. So this is 5 factorial divided by 4 factorial. Which is 5. And there we have it. This is describing the number of different cells, but you can do this exact same calculation for any sort of Coxeter diagram corresponding to a polytope, which has one of these ring vertices. So okay. Okay then, so we can handle the 5 cell, we can handle this 4-dimensional simplex. So now we're ready for the real. Okay then, Okay, then, so we can use Coxeter groups to understand the structure of this four-dimensional simplex. That's pretty cool. But this is just a warm-up. Now we're ready for the real challenge, which is understanding the tetrahedron. Well, okay, yeah. So we've already done something harder, so now we can come back to so we've already so basically now we've done the 4D case, we can come back to the 3D case. And we're just going to do the same thing here, but now it's going to be a lot easier to understand exactly what's going on. And I really think this is very beautiful maths because we're seeing a lot of different ideas combined here. So what we want to do is to understand what this Coxeter diagram means as a regular polytope. And so we know that the edges should be labeled with the number 3. And we know that there are 3 nodes. So we know we're working with something in 3-dimensional space. And we have this ringed node here. And so if we want to find out what the 2-dimensional faces are of this polytope, we just look at this and we just look at the shape of that and we recognize that means triangle. Yeah, because we're talking about this, which is this, which is the triangle. Okay, so that's why we have a triangle here. Now, what does this mean in terms of the geometry that we were discussing earlier? Well, basically, you can think of W0, W1, and W2 as elements of this Coxeter group. And then here we're looking at the subgroup generated by W0 and W1. And you can think of those as sort of drawn in this picture here. We were discussing this earlier. Um, So this is the symmetry group of the entire tetrahedron that we can get generated by W0, W1, and W2. But if we only use W0 and W1, basically, we're just talking about the symmetries of the tetrahedron, which are going to, well, literally, they're going to be the ones that leave O2 fixed. You see, O2 stands for this triangle of this tetrahedron, which is closest to us. You see, the positions of O0, O1, O2, and O3 give us something almost like a basis that we can use to refer to specific geometric elements, and then we can look at the sort of reflections of those. So I call these things primordial cells. So there's this like O0 is the primordial vertex. The edge through O0 and O1 is the primordial edge. The face holding O0, O1, and O2 is the primordial face, and so on. And those basically, you can encode those in terms of the subgroup of transformations that leave those points fixed. Um, so, okay, what's going on here? We have these basic permutations, W0, W1, W2. You can think of these as permutations of a set of 4 elements. And these correspond to reflecting in these different planes, the red, blue, and green ones. And we can use those basic symmetries to get all the symmetries of the tetrahedron. And so if we look at this picture, we've only got W0 and W1. So this means the subgroup of the symmetry group of the tetrahedron just generated by W0 and W1. So that means that we're only interested in reflecting in W0 or W1. Now, why is that? Well, look, look, O2 here stands for this face, which is closest to us. And that's our sort of primordial face, if you like. And what this is standing for is the symmetries which are leaving this face invariant. So we've already seen that if we have the symmetry group of a polytope and we know where O0 is, we can generate that polytope. So in a similar way, um, if we look at this subgroup, which is generated by W0 and W1, well, we know that both of those planes are going to go through O2 here. And we know that O2 basically corresponds to this triangle. A better way to look at this is that O0 is also a point of this triangle. And if we look at the image of O0 using just the red and the blue plane, what those sweep out are the vertices of this front triangle. And that's the sense in which W0 and W1 are operating on this ringed vertex here, which really corresponds to O0 here. Um, well, that gives us our sort of, we could call it our primordial triangle, this triangle here. Now, if we want to get, now the point is that this is really going to be now the point is that these symmetries that we can generate with the red and the blue plane are going to give us a subgroup of S4, a subgroup of the symmetry group of the whole uh, tetrahedron here. And so each triangle is going to correspond to one of these sort of left cosets here. And so the number of these is going to be the number of elements of S4, that's 4 factorial, divided by the number of elements here, which is going to be 3 factorial. So that's 4. That's the number of triangular faces there are of a tetrahedron. Each triangular face corresponds to a left coset of the thing that's generated by this. And if you want to find out what W0 and W1 are, you can see them as permutations of the elements 1 to 4 here. So that tells us this. Sorry, I meant to put this number should go down here actually. So we're making very good progress. How to we've understood the triangles within the tetrahedron. And basically the way we did it is we looked at our Coxeter diagram and then we looked at the subgraphs of it that contain the connected subgraphs that contain the ringed node that have 2 vertices. Now, in a similar way, if we do that for things that have 1 vertex, we can consider the edge. But we want to get that structure from this original structure by doing as little damage as possible. So we're just going to knock out W1 here, and that gives us this. But it's only the connected component with the ringed vertex that tells us the actual structure that we're dealing with here, which is just a single edge. And so to work out the number of these edges within our tetrahedron, we want to do this divided by this. So this has 3 nodes in a chain, so that's 4 factorial, and this is 1 and then 1. So 2 factorial, 2 factorial. Is 3 factorial is 6. But, we can think about this in terms of group theory. So we can get this group times it by this group. That's the meaning of having separate connected components. Anyway, this is a subgroup of this. It's the subgroup of S4, which is generated by W0 and W2. So it's going to be a subgroup of this. And the number of elements it has is written like this. And then the left cosets, sorry, the number of elements that this subgroup has is here, 2 factorial divided by 2 factorial. And then this number here counts the number of left cosets of this thing here, or, the thing generated by these, when we, apply elements of S4 to it on the left. And that's sweeping out the different edges. But then what's the meaning of this? Well, basically, we can understand this a little bit in this situation here, because what these really are are the symmetries that are leaving this sort of primordial edge invariant. What I mean by that is that for the primordial edge, we draw the edge through O0 and O1. Let's call that edge E, for example. So how can we talk about this edge? Well, firstly, we can associate it with the symmetries that leave it invariant. That gives us a subgroup, and then we can look at these different left cosets that move that around. So that's the basic idea. But what kind of symmetries leave this thing invariant? Well, this thing is going to be invariant under the symmetry W2 because the plane W2 contains this edge. That's not going to do anything to the edge. Like the edge is inside the mirror. It won't be moved at all. On the other hand, W0 actually flips the edge around, flips one and two, but it sends the edge to itself. I mean, but it doesn't. The vertex set is flipped around, so we have W0, which is giving us an actual symmetry of this structure, this edge, and W2, which is another symmetry under which this structure is invariant with, but it's invariant under that because it's contained within that mirror. So these are different sorts of things going on. And a similar kind of thing extends um, when we look at other examples, when one sees other examples. Anyway, let's finish the job. How many vertices? 4 factorial divided by 3 factorial is 4. And you can kind of see that this diagram looks like this diagram. So now I want to show something else, which I think is pretty interesting. It turns out that if you take any Coxeter diagram, let's say it's telling you the symmetries of some regular polytope or something, well, you can actually ring any vertex, and that's going to mean something geometrically. So what does it mean? Well, since we're sort of in the neighborhood, so to speak, why don't we look at this example? So we're going to ring this vertex here now. So remember, if we ringed this vertex here, that would mean a tetrahedron. But now we're going to ring this. So what does this mean? This is what we have to try to understand. So we're going to apply the same method that we did before. So firstly, we ask, what are the different connected components of this graph that have 2 vertices? And there are 2, I just showed them. So let's draw out those. So, okay. We look at these different possible. So, okay, we look at these. So, okay, we look at these different possible subgraphs. This one here, which is here, and the other. And we're just going to compute out what the structure of this thing is. So, do we know what this is? Yeah, sure, this is a triangle. Same for this. And so these are telling us that there are 2 different families of faces for whatever this polytope is, polyhedron. Um, but they're both triangles. So we have 2 different families of triangles. Okay, how many members do these families have? Well, this is a chain of 3 vertices. So that's 4 factorial, 24, the number of symmetries of the tetrahedron. Okay, that's that divided by this, which is this is 2 dots, so that's 3 factorial. That's four. So we've got four triangles in the first family, and similarly, we've got four triangles in the second family. Okay, what else? Well, we just thought about the size two subgraphs that are connected. Now let's talk about the size one subgraph. Well, that would just be the one that just has W0. So what's the least amount of damage we have to do to this to get that? Well, we have to delete these two. And so the resulting Coxeter diagram, it just has W1, and this is ringed, and it corresponds to an edge. And there it is. How many of these are there? Well, it's just this divided by this. So it's 4 factorial divided by 2 factorial. Which is 24 over 2, which is 12. What shape are we talking about here? Let's carry on. So now we want to consider a vertex. So which Coxeter diagram is that? Well, we just want to get rid of the ringed vertex. So if we do that, then we end up with W0 and W2 left behind. Now, how many of these are there going to be? Well, it's 4 factorial divided by 2 factorial, 2 factorial, because that's that many. So that's going to be 6. And so there you have it. And you know what shape this is? I hope so. It's the octahedron. So now you can take any, let's say, a regular polytope, for example. You can write the Schlafly symbol, PQR. And you can say, okay, that means the same as this. And now if you want to do what's sometimes called the rectification or the truncation of that regular polytope, you can just say it's this. Here. And then if you go into this and you compute its structure, applying the same methods that I've just been showing, you can find out that it is this is corresponding to this notion of, I think I was calling it truncation in the perfect shapes video. It's a very important and interesting thing that you can do to these regular polytopes. You can take one and you can form another polytope, the vertices of which correspond to the centers of the edges of the original regular polytope. So if you do this, it's really fascinating. You can get things like the 24 cell as the truncation of the 16 cell, and also the truncation of the 5 cell is very interesting. But yes, so this has been stuff to do with really trying to understand, from my perspective, something that I think's going on kind of behind geometry in a way, which is basically to do with these Coxeter groups and symmetries and representations. But it all happens very naturally. We're not going to have to get bogged down into very much theory, because basically this has culminated in um, an algorithm or two that I've written in Mathematica, which basically do this Wythoff construction. I'm not sure if I'm pronouncing that properly. Wythoff, I'm guessing is the right way to say it, but I'm not sure. Anyway, um, here's some code that basically calculates this 142 Gosset polytope, which is one of these 8-dimensional polytopes with this E8 symmetry group. And this is some code that we'll be talking about later, sort of how it works. So the idea is really that in Coxeter, he has this way of describing polytopes in terms of kaleidoscopes. So, you know, the idea of a kaleidoscope, you get a load of mirrors that are in certain configuration. And then what you can do is you can light up a single point. Like imagine putting like a single LED in a mirror house or something. And then where all of the reflections of that thing look like they are, gives you a shape. And that can be thought of as the vertex set of a certain regular polytope. So the idea is basically to literally use a kaleidoscope to package a description of the symmetry of these shapes. And then these descriptions of these kaleidoscopes translate with these so-called Coxeter graphs or Coxeter diagrams. So these ADE graphs that I've been mentioning quite a bit in recent videos, that's what they are examples of. So this 142 polytope is pretty interesting, I think, because there are several of these polytopes associated with E8, and I think more commonly studied is I think it's the 421 Gosset polytope, um, the root polytope of E8, because that's, well, it just appears more naturally from the um, sort of lattice theory. And in some respects, it's a simpler kind of polytope. This 142 polytope, on the other hand, is actually quite interesting in the sense that it sort of contains lots of the other polytopes of lower dimensions of different flavors. Um, so, so yeah, it's actually the first picture in this book I'm writing. But you can see this E8 142 polytope at the bottom left here. This is the number of elements in its symmetry group. Um, 696729600. That's a big number. Um, and we can see that it has 7-dimensional cells which look like E7 and D7. And, you know, there's a lot of, and then we can go into those. But because of the particular, I mean, this is all stuff that isn't, you know, we'll get into what all this means later. But because of the particular node that we ringed, and because in terms of this lattice, that ringed node makes sense all the way to the top, it means that um, this particular polytope has um, very interesting properties, I think. Um, but anyhow, um, let's get to the basics. So, um, we're interested in shapes and symmetries, and like, so we're interested in shapes and symmetries because they are essential to understanding all sorts of things, it seems. And so, if we think about something like a regular triangle, we can think about the symmetries that that has, and we can learn about that and what that means and how we can how those interact with each other and so on. But there's also another way of looking at it where we can really actually get the triangle from the symmetries themselves. So this is a curious thing that happens in group theory, is that um, you can look at things in such a way that the shape itself is sort of secondary and the symmetries of the shape are primary. And what I mean by that is that basically, if like a kaleidoscope where you have like a load of mirrors arranged in a particular configuration, or like imagine like a room with loads of mirrors in different directions that's say dark, and then you light up a single point and you see all of the sort of images of that lit up LED, let's say, in the mirrors, and it looks like there's some configuration of points around you. Well, that's the kind of idea behind something called if I can spell this, it's um, the Wythoff construction. So this is basically what the Wythoff construction is. It's essentially saying that if you have some, well, firstly think about something like what we could call a honeycomb. Okay, so we could actually have like a literal honeycomb pattern. And this is a tiling of three-dimensional space, right? So how can we, sorry, of two-dimensional space. This is a tiling of two-dimensional space, and how can we describe this honeycomb? Well, we could say, okay, we're using hexagons, okay, six gons, these 2D shapes with six sides. And then how many of these are there meeting every vertex? Well, there's three. So we can write this. It's called the Schlafly symbol. And this is basically describing the nature of this kind of honeycomb pattern. Now, I say honeycomb. Honeycomb in this kind of hypergeometry or whatever subject it is we're doing. This word honeycomb means something more generally. So, more generally, what it means is something that goes on forever, and we talk about regular honeycomb patterns. So, it's like this is a regular honeycomb pattern because it's infinite, it extends forever, but it has this complete symmetry where every cell looks like every other cell, every vertex looks like every other vertex, etc. And we know that there are other regular two-dimensional honeycomb patterns by this definition. One of them is this square grid. And there we can see, okay, we have four gons. And how many of them are there meeting at a vertex? There are four. So that would be the Schlafly symbol for what we could call the square lattice. And then there's another one which we can get by dualizing this lattice here. So we just draw a vertex in the center of every face. And we get this triangular lattice now. And so here we see that we're using these three gons, and that we have six of them meeting at every vertex. And incidentally, you can see that this Schlafly symbol is the reverse of this Schlafly symbol, and the green pattern is the dual of the black pattern. And usually, well, always when you have that kind of duality, it implies that Schlafly symbol has that kind of you reverse it to get the dual, that kind of thing. So you can imagine getting patterns like these two-dimensional ones by putting mirrors together. You can put two or three mirrors together and then light up some light and see all the images of it, and they can appear in um, hexagon pattern and all sorts of things. I think to get this hexagon pattern, one way you can do it is if you just get 3 mirrors, um, sort of arranged in an equilateral triangle. And then if you light up, I think if you just light up then one of the vertices and you see the images of that, I think that will appear in a hexagonal pattern. Um, Now, the thing is, for each of these cases, we actually have a sort of Coxeter diagram which describes that situation. But I think it's better actually for me to start with finite shapes. So, I mean, we can think of this um, infinite hexagonal honeycomb pattern as like a single shape. And what we're doing is we're filling the plane with hexagons essentially. Um, but if you wanted to try and fill two-dimensional space with pentagons instead, those would have to close up to form a sphere, to form a dodecahedron shape. So here's a picture of a dodecahedron, and you can see that in this case we have these 5 gons here, and there are 3 of them meeting at a particular vertex. So the Schlafly symbol for the dodecahedron is 5, 3. Okay. And of course, there are other what we call platonic solids or two-dimensional regular polyhedrons. And you could think of these as kind of other tilings of the sphere, if you like. Okay, so yeah, let's talk about another one which is important. It's the cube. So try and guess the Schlafly symbol for the cube. Well, it's made out of 4 gons. The faces are squares, those are 4 gons. And then we have we have 1, 2, 3 of those meeting at every vertex. So the Schlafly symbol is 4, 3. Another one that's going to be very important for us is the tetrahedron. And so in this case, the faces are triangles, and we have 3 of them around any vertex. So the Schlafly symbol is 3, 3. Okay. And, later we're going to be thinking about things like hypercubes, for example, which is a nice case of a 4D regular polytope. Maybe the easiest one to study in some ways. Although the 5 cell's also worth having a good look at. But yeah, so with the tesseract here, or the hypercube, it has these 8 different 3D cells. So there's one in the middle here, then there's 6 around the outside, one for every face of a dice, and then the very outside of this is also considered to to be a 3D cell. Because what I'm doing here, this is a 2D picture, of course, of a 3D, of a projection of a tesseract into 3 dimensions. And because it's projected like this, because it's projected like this, the very outside of the space is sort of like the eighth cell, very much like if you were to um, draw this pattern here on a big basketball or something. You could say that's a sort of distorted cube, because you could imagine if this was made out of some kind of more plasticky thing that was stuck to this sphere, you could morph it round so that it actually looked like a cube. If you pulled this back round, imagine this is drawn on a ball, and then you can pull this round, you can make it look like an actual. But you could make it look like a cube. Anyway, now, so the Schlafly symbol here, what's the Schlafly symbol for this 4D shape? Well, what are these 3D cells? What kind of shapes are they? Well, they're cubes. What's the Schlafly symbol for a cube? 4, 3. And how many of these three-dimensional cells do we have around a particular edge? The answer is 3. So the Schlafly symbol for the tesseract is 4, 3, 3. So that's how you do it for these four-dimensional things. The first two numbers are describing the kind of cells you have, and then the third number is saying how many cells are you like that you're going to have touching any particular edge. So if we take any particular edge in this tesseract here, we'd say, okay, how many 3 cells are there touching this edge? Well, there's going to be the 3 cell that's sort of directly in front of us. There's this 3 cell here, and there's this 3 cell up here. So there's 3. Maybe an easier one to look at is this. No, I think. Anyway, yeah, maybe this is an easier one. Yeah. So here the three cells touching this edge are the very, very center of the picture. The cube down here and the cube here. So yeah, that's the number of 3 cells that are touching a particular edge, and that's the Schlafly symbol for the 3 cell, and that's the general pattern. So more generally, if you have a regular polytope in 4 dimensions, and you say Schlafly symbol is PQR, that means that the 3-dimensional polyhedra that form the cells are PQs, and we have R of them around any edge. So that's telling you how many of these 3 cells there are around a particular edge, or touching, that edge being the boundary of those. So there we are. Okay, so what does any of this have to do with these symmetries? And what's it have to do with Coxeter groups? Well, Coxeter groups are an interesting thing to, like, yeah. I feel like with category theory or something, it sort of, that subject describes itself. So, if you want to, get across some category theory ideas, you can just tell people enough category theory, and then the sort of language just overflows. But with these Coxeter groups, these are more like, they do very particular, very kind of delicate things, but those things are, I think, fundamentally important for how the mathematical universe works. So it's more like um, describing almost like an alien programming language or something, um, which is used to do the geometry. Um, and in that way, I think it's good that we start just by getting familiarity with the basic symbols that we're using here. So we have these Schlafly symbols, and basically, let me just start by showing you how we can translate each of these Schlafly symbols into a Coxeter diagram. Okay, so for the dodecahedron here, the Coxeter diagram is this. For the cube, again, I say Coxeter diagram. Actually, the Coxeter diagram or Coxeter graph would just look like this. It would just have vertices and edges, and the edges might have labels. And it would be a simple graph of some kind. But I'm also going to ring a particular vertex, and what this is denoting, I'm just going to say, this won't mean much at the moment, we're going to come back to this, but what this ring is denoting basically is that we're performing something called a Wythoff construction, as is described in Coxeter's regular Polytopes book, I think in chapter 11. Now, for the cube, this is the Schlafly symbol, and you can see now how. Sorry, this is the for the cube. This is the corresponding Coxeter diagram, and you can see how to do this now. How we're going to get the diagram for the tesseract. We just write down what's on the Schlafly symbol, and if we have a regular polytope in 4 dimensions with Schlafly symbol PQR, well, the corresponding Coxeter diagram looks like this. So what we're going to see eventually, it's going to take a while to get to it, but eventually we're going to see that this really is telling us the same amount of information as this. In fact, what's going on with this, what we're going to see is that this picture here is really a recipe for constructing this regular polytope by reflecting around these mirrors in higher dimensions. And this whole story extends to a general number of dimensions, and this is the sort of backdrop where we can look at questions like, oh, what are all the symmetries, or what are all of the sort of perfect shapes in different ways, or what are these exceptional structures in 8 dimensions, these E8 structures, and all this kind of stuff. Well, I mean, I personally think that this sort of Wythoff construction thing is in the center of this, but it's going to take us like a little bit of time, maybe 20 minutes or so, to get to the point where we can sort of where we're familiar enough with these Coxeter diagrams that we can do this. So yeah, so what we need to do is do this sort of triangle symmetry. stuff. Um, maybe also the cube symmetry, and then we can describe the linear algebra of this, how there's a formula for the reflection and things like that. And we can also describe this lattice stuff, and then we can get into the DN code and maybe the AM and the E8 code. So I think that's a good plan. This is where it all comes together, in the sense that, as we understand, and it sounds a bit pretentious, but I think it's true though, that as we understand what these Coxeter diagrams are, we understand a kind of confluence of lots of things all coming together at the same time. Basically, a full understanding of what symmetry means in terms of shapes and how that relates with linear algebra and geometry and where shapes come from. I think that, in a sense, all of this, in my opinion, is encoded in this kind of idea of the Wythoff construction. And I'm going to describe this for an equilateral triangle, but exactly the same kind of idea works in general. Now, there's a way we can use this to make a triangle. That would be the Wythoff construction. There's another way we can use it where we take an equilateral triangle and then we get the symmetries of it. So we're going to do the latter because it's easier to think about to begin with. So let's draw an equilateral triangle. And what we're going to do, I think this is called a flag, but it's a certain sequence of points that we're going to pick in this regular polytope, which are going to be very important for us. And so this description I'm about to give is really important, and you should really bear in mind that this could work for any regular polytope in any number of dimensions. So you could do something analogous to this for a hypercube, a tesseract, a four-dimensional cube. In that case, you'd be working in 4 dimensions, so n, the number of dimensions, would be 4. In this case here, the number of dimensions, n, is 2, because we're looking at an equilateral triangle. So, here's the idea. This is how we make what we're going to call a flag. We pick any vertex. We call that vertex O0. This 0 here stands for 0-dimensional. Now, we pick any edge which is touching this vertex. Let's say we pick this one. And we're going to mark the center of that, and we're going to call that O1. So, a vertex is a 0-dimensional cell. An edge is a 1-dimensional cell. The next step, we take a 2-dimensional cell which is touching this edge, and we mark the center of that O2. And if there were higher dimensions, we would carry on. We would look for a 3-dimensional cell that has that as a boundary, and then we'd mark the center of that O3, and we would carry on. But in this case, now we have this point O2, we're done because we only go up to n. So basically this idea is that we can take our regular polytope. What do I mean by regular polytope? I mean a shape in n dimensions that's as symmetric as possible. So think about something like a tesseract, a hypercube, that kind of thing, or a square in 2 dimensions. So we take our regular polytope, and then we get this flag, So we've got these points O0, O1, all the way up to ON. And what about these points? What are these doing for us? Well, one thing about having 3 points in the plane, usually, is that they're going to give you a triangle. And we can look at that triangle, and in fact, that triangle is going to be essential for us. So actually, I want to colour the triangle a bit differently. Let me colour this edge red, so I can extend this line as much as I like. And then I want to make this edge blue. So, what's going on here? Well, basically, the short answer is, let's call this region here the fundamental region. Let's imagine that we put something here, something that we want to look at. So maybe we have a little model man here, and we put it down, and then we think of this as a mirror, and we think of this as a mirror. And so we have a sort of kaleidoscope. We have these two mirrored walls. This angle here is pi over 3 radians. That's 60 degrees. And, you know, if you just get two mirrors at 60 degrees, you can see that you're going to make some kind of a kaleidoscope happen. And in fact, you're going to see reflections of mirrors in mirrors, and basically we're going to have a sort of virtual mirror, if you like, which is going to appear like this, and it's going to look like we're sort of cutting things up into 6 different things. So we have our sort of fundamental region here, where we can put something that we want to reflect around, and then we can look at the images of it, and the image over in this chamber here is going to have the left and right side reflected around. So, you know, if we did something to our original triangle, maybe I won't give it such suggestive colours. Yeah, if we had a colouring of our original triangle, then the image over here, the purple and the orange would be reversed round. Anyway, I won't use colours like that. Not in this picture, I've done it before. So this one here would be flipped over like this. So we can really see this blue line here, since if we think of it as a mirror, it's really having this effect of swapping around. Like if we number these vertices 1, 2 and 3, then this is really swapping around 2 and 3, if you like. On the other hand, this mirror here is having the effect of swapping around 1 and 2. And so it turns out that you can then say, okay, what happens if we take this, which is corresponding to a certain kind of reflection? I mean, really, if you think about, imagine this triangle is in the plane and the origin is here, you can think about this as a sort of linear map from the plane to itself, and we can say, okay then, well, if we have this and then we reflect it in this mirror, we should have something that looks like it's over here, and this is going to correspond to another transformation, the transformation we get by doing this sort of 1-2 swap after this 2-3 swap. And so what's the result of this? Well, if we started here, for example, firstly we have to do this operation, so we have to go up here, and then we have to perform this operation, but that wouldn't change it. So we know that in the results, this point here gets sent up here, and I know that composing two different reflections like this is going to lead to a rotation that looks like this. And that turns out to be the result here. So we should draw that in here. And we can just finish this off. Happy little triangles. There we go. So we've got these 6 different chambers, 6 different symmetries of the triangle, and they're being described by this kaleidoscope pattern here. And we can even name these mirrors, okay? This is a good thing to do. So let's call this mirror W0 because it's sort of opposite O0. So what you should really think about now is this triangle here with these 3 vertices. This is our fundamental region. This is corresponding to the identity in terms of each of these 6 chambers here corresponds to a different group element. Just the same kind of thing would happen in higher dimensions and in general. So you can see that what we're really having here is a sort of simplex. We have these n+1 points here, O0 all the way up to On, and then we can take, for example, O0, and we can look at the wall opposite O0, that's W0, that's the kind of hyperplane that goes through all of the O points apart from O0. And similarly, there'll be this blue one here, this would be W1. And you can imagine in higher dimensions, if we have some regular polytope P in, let's script P in n dimensions, well, we can make a flag and get these points O0, O1 all the way up to On. These are going to form an n-dimensional simplex. So it's a sort of higher dimensional analog of a triangle. Probably not a regular simplex, but the point is that for each I from 0 all the way up to n-1, we have that Wi is going to be the n-1 dimensional hyperplane through, and it's going to go through each OI which has I not equal to and that's going to go through each OJ which has J not equal to I. Okay, so it's just basically the same idea as what I'm showing here. I'm just saying that n-dimensional kind of analog of that. And so you can see that what's going on here is kind of fundamental, and what's even cooler, and I'm really condensing a lot here because I've talked about this at great length in that perfect shapes video, and I don't want to repeat myself too much, so I've tried to just give the sort of bare basics that one would need to follow this. But I think if you watch the first hour of that perfect shapes video, that gives a much more, maybe the first hour and a half of it, that gives a much more paced introduction to these Coxeter groups. But the main point here is that if we then took a mirror here and a mirror here, and we have this as our region, and we put our object here at this actual vertex, And then we looked at the image of it in the mirrors. Well, if we reflect it in the red mirror, we get over here. Then if we reflect in the blue mirror, we get over here. We've already got our vertices of the triangle. And this is the idea of the Wythoff construction. So now I'll tell you what the Coxeter diagram is for the triangle and where it comes from this picture. So we have O0, or equivalently W0. Okay, you can kind of see that information-wise, this line here and this point here, they kind of go together. So we can call the first vertex of our Coxeter diagram red, and let's call it W0. Normally the vertices aren't named and they aren't coloured. I'm just doing this to help with understanding. So the other vertex, we're going to call it W1. And now we're going to link these two vertices, and this edge, we're going to write a number 3 on it. And this is the Coxeter diagram of the triangle. Well, it's the Coxeter diagram for the symmetries of the triangle. Actually, if we want to get the triangle itself, we also ought to ring this. And if we ring this, this is then describing this Wythoff construction, which I just told you what it was. We light up this vertex and then we see where it reflects in the mirrors, and that gives us the vertex set of a triangle. So that's what this would denote. This would denote a triangle in this case. But we can also just consider this diagram here, and this diagram by itself. What this is really describing for us is it's describing the symmetries of the triangle itself. So this is really describing, in a sense, it's describing the symmetries of the triangle. Why is this significant? Well, because if you think about things like a cube in 3D or an octahedron, well, those two shapes are dual to each other. They're symmetry-wise, they're kind of the same as the cube and the octahedron. They have the same kind of symmetries because they essentially, they're kind of like they basically look like each other in disguise to the cube and the octahedron. And so you could think about the symmetries of both of those, and the symmetry group in some sense could be considered more fundamental than the cube or the octahedron. And these are the kind of things we can get at with these Coxeter diagrams. So I say that this is describing the symmetries of the triangle. Well, how? What does this diagram mean? Well, notice that the angle between the blue line here and the red line is pi divided by 3. Well, that's why there's a 3 here. Okay, if the angle between this blue and green was pi divided by 7, then we'd be writing a 7 here instead. So this is basically telling us an angle, and then this red dot here stands for this red mirror, or this red hyperplane more generally, and this blue dot here stands for this blue hyperplane. So more generally, if we draw a more general kind of Coxeter diagram, for example, let me draw one for the cube. I'm just gonna draw something quick. There we are. Well, more generally, these these different nodes here, I'll call them W0, W1, and W2. Well, in this case, okay, so how do we read Coxeter diagrams? Let me tell you this now. So we have enough background. I'll just tell you how we read these things. So, firstly, how many nodes do you have? That's the first question. That tells you how many dimensions of space you're working in. Okay, so in this case here, with this diagram at the bottom right, we have 2 nodes, so we're working in 2 dimensions. in this case at the top left, we have 3 nodes, so we're working in 3 dimensions. Okay, that's the first thing. The second thing is, what do the nodes mean? The answer is the nodes basically correspond to n-1 dimensional hyperplanes. Okay, so we're in n-dimensional space if we have n nodes altogether, and every particular node corresponds to an n-1 dimensional hyperplane. So in this case here, n is 2 because we have 2 nodes, so we're working in 2 dimensions, and each of our nodes, like the red one here, corresponds to this n-1 dimensional hyperplane. Well, n is 2, so n-1 is 1. So this is a 1-dimensional hyperplane, so it's a line. So that's cool. More generally, yeah, we can have situations like at the top left. So what's this then? Well, in this case, we have 3 nodes, so we're working in 3-dimensional space, and each of these nodes is going to be a 2-dimensional hyperplane. So in this case, we're working in 3D, and this is going to be a plane, and this is going to be a plane, and this is going to be a plane. Okay, so we have some situation in 3-dimensional space where we have 3 planes that are called W0, W1, W2. Fair enough. But what do we know about them? Well, what we know about them, and what this diagram is actually encoding for us, is the angles between these different planes. Okay, so if you have 2 planes that are cutting each other in 3D space, there's going to be a sort of dihedral angle between those. And what this diagram is telling us, okay, so this diagram, there's something about Coxeter diagrams that you might not know. And there's a bit of a secret about them. And the secret is that when you have 2 vertices that are not linked in a Coxeter diagram, you should actually link them, and you should write a number 2 there. So basically, an absence of a connection really signifies that there should be a connection there with a number 2 on them. So every pair of vertices, distinct vertices, has a connection with a number on it, really, in the actual structure. It's just that for some reason, which we'll see later, you don't really want to write these links which have 2's on them, and so people don't bother writing them. So this is really the picture that we have. This is really the Coxeter diagram for the cube, if you like. So what is this telling us? Well, we have these 3 planes here. Okay, let's make a little picture. We're in 3D space. Somehow we have these 3 planes. And what else do we know? Well, we have these numbers here, and what these numbers are telling us is they're telling us the angles between these different planes. So this is W0, let's say. This one here. And let's say this one here is W1. So what's the number on the link between W0 and W1? Well, it's 4. That means the angle between these 2 different planes here is pi divided by 4. And so that's, you know, that stands for pi divided by 4. This stands for an angle of pi divided by 3 between W1 and W2. There's an angle of pi divided by 2 between those 2 planes. That means they're perpendicular, and in some sense that indicates some kind of independence, which a lack of a connection in a diagram is appropriate to signify, but let's not worry about that now. The point is that what this diagram itself is really conveying is a way of laying out mirrors, essentially a way of making a setup which is like this setup here, but possibly in higher dimensions. It's a way of telling you how you can set up your mirrors so that you've got your fundamental region. And that's basically what your Coxeter diagram, without a ringed node, is telling you. So this is your Coxeter diagram, and we can see now that if we know about these mirrors and how they should be laid out, then they're essentially going to generate the symmetry group of our regular polytope. So this is why it's a way of encoding the symmetries. This is a so-called Coxeter group, or it's a way of getting at the symmetry group of a regular polytope. But there's more to it if you ring a particular vertex, because now what's essentially happening is that you can ask where the image of that vertex. Sorry, what am I trying to say here? Say we ring a particular vertex. This actually stands for a particular geometric shape. So, which geometric shape is it? Basically, what this is it's the images of O0 in this kaleidoscope. I'm not going to bother trying to spell the word kaleidoscope. It's probably a hard word to spell, but that O0 will reflect around in that. So the point, more generally, if someone gives you some Coxeter diagram, which could look like anything, well, let's just stick with what we know. Let's say P, Q, R. Something like this, let's say. You say, okay, this is the ringed node. We could say this is corresponding to the hyperplane W0. But, these hyperplanes are really formed from this sort of simplex. So you could equivalently say this is referring to O0, which is like the sort of vertex, which is opposite W0 in this simplex. Okay, so we're going to have a situation, again, very similar to this one, but in higher dimensions. So we could say, okay, yeah, this is W0, this is W0, but when we ring this, we really mean let's look at the vertex that's opposite W0 and see how that's going to get reflected around in this kaleidoscope. And that's giving us this Wythoff construction. Like physically doing that would give us our regular polytope. It gives us the vertex sets. And we're going to see later there's other things we can do involving group theory as well, so that we can really dig in and get at the sort of combinatorial structure of our regular polytope. But yeah, okay, so I'm really going for a minimalistic introduction to this Mathematica code that I've written, which calculates, what's it calculate? It calculates the structure of, it does Wythoff constructions. So this Mathematica code does Wythoff constructions for dn graphs. And it's, something similar would work for most of the other cases as well. So this is really, this code is, to me, but I think there's a lot of geometry behind this code that's very interesting. So I want to try and introduce this as quickly as possible. Now, I've just introduced this idea of Coxeter diagrams, so let me just jump straight into this. So mostly the Coxeter diagrams we've looked at so far have this kind of form, P, Q, and then this node on the far left is circled, but we can have more general things. So we're going to now start considering Coxeter diagrams with this kind of shape. So here, this dot 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 here is just meaning that the dots go on. So we're going to actually number these dots, 1, 2, 3, 4, n minus 2, n minus 1, and n. And this is what we call dn. It's a graph with n nodes that are almost all just in a path, but there's this little sort of fishtail at the end here. And then what we're going to consider is dn graphs where the first node is ringed. And what we're really doing here, what this is denoting, is this Wythoff construction. For what shape? Well, the shape is an n-dimensional demicube. Okay, so I'd like to add a little announcement here. I discovered a mistake in the video at this point, and that is that this diagram I'm showing here, where the far left vertex is ringed, is, I think now, not giving us the n-dimensional demicube. I think that what I should have done instead was ring either vertex n or vertex n minus 1. You know, the I should have ringed one of the vertices at the fishtail instead. But I didn't. I ringed that vertex on the far left. So when I say this corresponds to an n-dimensional demicube, I think that might be wrong in general. Now, in the case that we investigate where n equals 4, it turns out to be true anyway. So that's a sort of coincidentally, it doesn't matter in that case. So everything's fine with what I talk about, except when I say that this structure leads to the n-dimensional demicube. I'm not sure that's true now. I think it's not in general. So what structure do we get in this case? Well, we get the structure that I describe. I'm just not sure that that's the n-dimensional demicube, and that's not really important. I was more interested in the algorithm, the connection with the vectors, and the way dn works. And I still think all of the stuff I talk about there is correct. It's just that I made this mistake of basically ringing the wrong vertex to yield the n-dimensional demicube. So ideally, I would like to rework this video and work with a different Wythoff construction where a different vertex is ringed, one of the sort of fishtail vertices instead. But that's a lot of work, and I was mostly just interested in demonstrating how the approach works in general. So the fact that the diagram I've chosen to work with may not always yield the n-dimensional demicube is not really the point. Whatever it yields, I'm showing how we do the computations and think about how it works, and I still think that's valid. So sometimes that's a regular polytope, sometimes not, but it is a polytope, and we can get at it by this same kind of Wythoff construction. And so now I want to describe how we do this, because really the way that we do this is it's just works the same way in general. Okay, so what are the steps? Well, firstly, each of these nodes here, we want it to end up corresponding to a sort of hyperplane, right? So we want to give this, let's call these hyperplanes W1, W2, you know, this would be Wn minus 1. So in general, Wi is going to be some n minus 1 dimensional hyperplane. So it's going to be n minus 1 dimensional. So what's that mean? Well, one thing it means is that to determine where the hyperplane is, we can just give a non-zero vector. So what we do is each of these vertices is associated with a vector. So alpha 1, alpha 2, this would be alpha n minus 1, sorry, alpha n minus 2, excuse me, alpha n minus 1, and alpha n. Now, each of these is just going to be an n-dimensional vector. So, which vector is this? Well, this one here is going to be, let me get this right. Yeah, it's going to be, I'll call it E1 take away E2. So what does that mean? Well, here E1 is this first unit vector, and E2 is this second unit vector. And so what this really is it's going to be 1 minus 1, and everything else is going to be zeros. I mean, if you want, we can write them as column vectors. We should probably write these as column vectors, but anyway, that's what this is. Alpha 2 here, it's going to be E2 take away E3. This is going to be En minus 2 take away En minus 1. This one here is En minus 1 take away En. And alpha n, this is the different one, this is En minus 1 plus En. So we associate each of these vertices here with these vectors, and then we take Wi to be the n minus 1 dimensional hyperplane through the origin, which is perpendicular to alpha I. Okay, so maybe I'll write that down. So Wi is the n minus 1 dimensional hyperplane through the origin in n-dimensional space that is perpendicular to this vector alpha I. So I really want to think of that alpha I as a column vector, actually. Let me just add some transposes everywhere. Yeah, so it's a column vector. So, that's basically what we want to do. But now what we actually want to do is this Wythoff construction. So we really have a sort of geometry problem on our hands. Like, how do we get these hyperplanes? Do we have to figure out angles between them and stuff like this? How do we know where to put our LED in this kaleidoscope once we've already got it and all the rest of it? So what we do here is pretty cool. So let's say you have a non-zero column vector W, n-dimensional vector. So that's like an arrow in n-dimensional space, and so you can imagine there's an n minus 1 dimensional hyperplane that's perpendicular to that, and then you can imagine using that to reflect stuff. So if this is W and you have a point V, then we can speak of the reflection of V in this hyperplane, which is perpendicular to W. So we're interested particularly in the case where this hyperplane here is actually going to be alpha I. And so we're going to be using this vector alpha I, forming the hyperplane that's perpendicular to that, and then reflecting in that. And that's how we're setting up our kaleidoscope. So when I just described these vectors here, that was a sort of way of introducing the hyperplanes that we're going to use, basically. So it should be then, if we have this non-zero vector, that we have a linear map from the plane to itself called S omega. And we do indeed have this. And the formula for it, it's going to send a vector v to this reflection of v in the hyperplane, which is perpendicular to w. And the formula for it, if memory serves, is this. So that's what this formula here gives us, S W of v. And you know, that's cool because we have this linear map, but also because it can be thought of as a n by n matrix. So this is really nice. If we have a basis set up, which we will have, you know, we have the normal Euclidean basis. Well, we've got this n by n matrix, and this is going to be good for us because this is giving us our linear transformation of n-dimensional space. But we can then compose these matrices easily, and we can compose all the different symmetry operations. You remember we did this kind of almost sort of combinatorially, if you like, with the triangle. You can imagine there are matrices, there are 2 by 2 matrices that are corresponding to these symmetry operations. And if we have the matrix for this one and this one, we can multiply them together. We can look at all the different ways that we can multiply stuff together, starting with those primitive operations, and we can get all the symmetries of our regular polytope. So we can use those as generators. This is this idea of describing a Coxeter group in terms of generators. So now, if we go to Coxeter groups on NLab, the definition of them should make some sense, right? So the Coxeter group having generators SI, so these are mirror operations. So when they say SI after Sj to the power of Mij, what they're really talking about here is that if we compose these two different reflections, that's going to give us a rotation, and we can only do that rotation so many times, and we end up coming back around. And how many times we do that, that's the, you know, if we're talking about pi divided by p, and p is the label of that edge, that p is telling us the number of times we can power that rotation before it turns into an identity. And that's what this is on about. So okay, I think we're ready now to take a look at. So okay, I think we're ready now to take a look at this code. So, what's going on here? Well, firstly, for some reason I was running this in the 4-dimensional case. Yeah, so I think I have to. Yeah, because we're looking at D4. Okay, so let's unpack this. So that means we're looking at D4. So we're looking at this. It has 4 vertices. 1, 2, 3, 4, like that. And we have the first one ringed, presumably, after checking the code in a second. And that means we're talking about the 16 cell. So we're going to be generating the 16 cell. So this is the jewel of the tesseract. How do we make a 16 cell? Well, we can start with a square in 2 dimensions, and then if we add a couple of points, connect those to everything we've got before, then we have an octahedron. That's the 3-dimensional version of a cross polytope. Then to get the 4-dimensional version, we just do the same thing again. We add a couple of points, now in the 4th dimension, and we connect them with everything that we've already got. And that's what a 16 cell is. It turns out it has 16 tetrahedral cells. But we're going to now get the vertex set for the 16 cell using this code. So, what's going on? Well, firstly, we say we're working in 4 dimensions. That's what NN is. Next thing we're doing is defining how reflection works. And then we're getting these unit vectors, these EIs, as I was talking about. Um, and now these basis vectors. So these are these alpha i's. So basis vec of k is alpha k. And now this is very interesting. This next part of code, I think this is by far the most interesting part of this code. Basically, what we're going to do is we're going to get some n by n matrices. So let's say they're A1, A2, all the way up to AM or something. And we're going to start with those matrices, and they're going to correspond to our reflections, like our red and blue lines from the triangle picture from before. And they're like our basic generators. And we're going to compose those with everything that's possible in all possible ways until we've run out of new possibilities. So the idea is basically that, like, if you imagine this LED that we light up in a kaleidoscope, it has to the photons have to bounce around all the mirrors. So we have to sort of do the symmetry operations on that on that LED. We can imagine doing them one at a time. Now reflecting the red mirror, now reflecting the blue mirror, now reflecting this mirror. And eventually we'd fill out all the possible images, or we'd gain all the possible symmetry transformations, much like with that triangle case earlier on. We just started with the red and the blue mirrors, and we just saw all the ways we could compose those, and we got all the possible 6 different symmetries of our regular polytope here. And you can imagine we could also do this with matrix multiplication. If we have the 2 by 2 matrix corresponding to this red thing and the 2 by 2 matrix corresponding to this blue thing, we could just multiply those matrices together in all possible ways. And we could just keep doing that until we stop getting anything new, and then we know we're done and we've squeezed all of the symmetry out from those generators. And that's just what we do here. So we're going to use those basic symmetries corresponding to those mirrors, and we're going to see everything that gets generated. And this update just does a single stage of basically you have a load of matrices, you get them, you multiply every matrix you have with every other matrix you have, you get all the new stuff that you get, you take that in union with the old stuff, so now you've got even more stuff. And we're going to keep doing that update stage until we reach a fixed point, and that's what this code does. So make cool here, it's a great name for some code. This is basically I was talking before about these matrices. So something like S alpha I, and basically this make cool gives us these matrices. So I think it's actually a K here, it's S alpha K. So it's going to give us the n by n matrix that corresponds to the symmetry operation that reflects in the hyperplane that's perpendicular to alpha K. So that oh, hang on. No, the make cool thing actually just gives us this actually, sorry, make cool doesn't do that exactly. What make cool does, actually, we supply any W and it gives us S of W. So then we're going to use that later with the alphas. I think that's what's going on. Yes. Yes, that's right. So make cool just turns any vector W into the matrix that gives the symmetry operation that corresponds to reflecting in the minus one dimensional hyperplane that's perpendicular to that vector W. And then what we're doing here is we're just applying that operation to each of our alpha i's. So this is basically giving us our set of original matrices. So essentially what I've highlighted here is going to be this set S alpha 1, S alpha 2, all the way up to S alpha n. These are our n by n matrices. These are corresponding to our basic symmetry operations. And then we're going to use those, we're going to multiply them with each other in all possible ways. And we get this thing called finished cool set, which is we're just going to keep doing that updating until we get a fixed point. Then we've got all the symmetries. And then all we have to do is we have to get a point and this is the subtle bit, this is the bit that stops me doing this for quite a long time, is we have to get a point that we want to reflect in all of this stuff. So let's think about that. So if we think about this as a simplex, then we're going to have each of these is going to be an n-1 dimensional hyperplane, and like we call these W1, W2, etc. We could have also labeled these with the vertices of the simplex, you know, the sort of vertex opposite this wall W1 here, and so on. Because we need to obtain the vertex corresponding to this, because this is what we want to reflect around in our hyperplane. So what do we know about this vertex? Let's call it O1 here. Well, what we know about it is that O1 is going to belong to the hyperplane W2, it's going to belong to the hyperplane W3, it's going to belong to all of the hyperplanes except for W1. And that information, that intersection of those hyperplanes there, is actually going to be a line. This is going to be a line. This is going to be a one-dimensional thing, like in general. And so we know now this point that we want to start with and reflect around, we know where that is up to a line. And so basically, what we want to do, I'm going to call it x tilde. We could also call it O1, but I like x tilde more as a name. So we want to get this point x tilde, and we want to have x tilde dotted with alpha 2 equals 0, x tilde dotted with alpha 3 equals 0, all the way up to x tilde dotted with alpha n equals 0. Why? Why do we want this? Well, this is equivalent to saying that x tilde is belonging to this hyperplane W2. Why is that? Well, because W2 is the set of all x in R to the n such that x dotted with alpha 2 equals 0. Okay, so I'm saying that we defined the hyperplane to be the set of all vectors that are perpendicular to alpha I. So, you know, perpendicular to the thing means when we dot it with that vector we get 0. So we could define the hyperplanes that way. So we have all of these equations, and if we just do it algebraically, it really defines what this x tilde should be, up to a multiplier because it's a line through the origin. But what we see in the code here is that it's sufficient to actually set this point to be E1. Okay, so in the end, after all that, we can just say, okay, actually x tilde equals E1 equals O1. That's the point that we're going to reflect around in this Wythoff construction. That's this point here, and we're going to reflect it around. So how are we going to reflect it around? Well, remember that we started out, we have this set of matrices here, S alpha 1, S alpha 2, all the way up to S alpha n. These are a load of n by n matrices, so let's give this set a name. Let's call it S. And then let's say S star is the set of matrices generated by these. I mean, we just take these and then we keep multiplying stuff in here. I better not call this S, actually. It's a bad name. Let's call it H. And then H star is the set of matrices generated by the set of stuff in H. So what we do is we get our sets of matrices that correspond to our primitive reflections. Let's call this set of matrices H. This is a load of n by n matrices. And we just get stuff in here and we keep timesing stuff in here by stuff in here and generate all the new elements and just keep generating new elements until we've got all the symmetries, and then we call the resulting set H star. And then finally, our Wythoff construction is just where we're going to multiply this matrix M by X tilde, and we're going to do that for every matrix M. And we're going to do that for every matrix M, which is in this set H star. And this is going to be the vertex set of this regular polytope. So that's the final conclusion of all this. Okay, so it's actually a really beautiful idea, which we can summarize now. So we want to make this 16 cell. So what we basically do is we get all of the symmetries that are sort of corresponding to this by generating them all, and then we get a particular vertex which we know is one of the vertices of it, and then we can apply those symmetries to reflect everything round in all possible ways, and that's how we can get our 16 cell. And so this works really well. I'm just drawing this nice little 2D 16 cell here. And yeah, so there's also this code here. So this tries to do the same thing for E8. So for this, let's go to the wiki about E8. So if we have a look here, where is it? Yes. So this is the golden part of the thing where they describe how you can get this E8 stuff. So this is the essential information. So it's just totally analogous to the case that we just did, except that now we're in 8 dimensions. But you know, these are how we should label the vertices: 1, 2, 3, 4, 5, 6, 7, 8. And then this is alpha 1, this is alpha 2, this is alpha 3, and so on. Each of the rows of this matrix giving us the different alphas, and we just proceed exactly as before. We can look at the hyperplanes perpendicular to those alphas, we get the corresponding reflection matrices, we multiply everything together, we get all the symmetries, we apply those to do the reflections that we want to do. And in this case here, we wanted to do it to get 1, 4, 2. So firstly, we get those vectors that I was talking about. So basis vec E8 just gives us the kth such vector. I also determined a point that was where I wanted it. So I've been interested in what happens when this is the ringed vertex. So I wanted a point that's on the hyperplanes corresponding to all the other points. So I did some math, and I found that this is such a point. So what I'm going to do is get all the possible symmetries and then reflect this point around in all possible ways using those different mirrors. Actually, we have to take a different route with the 8-dimensional case because it takes too many resources to do it that way. But that's if I had a really, amazing computer, that's the way I would do it. I'd get the entire matrix group and then apply all the symmetries like I just did for the DN case. But we can get well, that's just proving that our point has the right properties. And then this is getting our original set of matrices. And then, well, the way that we would do this, if we had an excellent computer, is we'd again use this updating procedure. And then once we've done that, we can just apply all those symmetries we have to that 0.08, and that's essentially like reflecting everything round. And that would give us our vertex set of our 142 Gosset polytope, which I just took this clipping from Wikipedia of. But the trouble with this is that that set of matrices is enormous. It's a huge set of 8 by 8 matrices, and my computer can't handle it. So what I do instead is to just have the vertices of this polytope being slowly generated as we keep applying all the reflections. So the way I've done it is basically that there are 8 possible reflections that we want to do, 8 possible basic reflection matrices that we want to apply. And so we can go through a round of applying each of those reflections in turn, and that would be like one round of reflecting. And we have this set of points that we're growing. So we start with just the point, where is it? Yeah, we start with just this 0.08 that has the right features, and then we keep doing rounds of updates until we stop getting new things. And when we do a round of updates, we just apply all the different possible 8 mirrors and look at all the new stuff we get in union with all the old stuff, and we just keep reflecting everything round until we've got all of the vertices of this Gosset polytope. So that's basically the approach. So all of this complements well this other approach towards the symmetries, which is involving cosets, which is totally complementary. But basically, like we've just been thinking about this 16 cell case here that's pictured, and we can see that this is the Coxeter diagram for the 16 cell. The thing is, if we look at the different sort of subgraphs of this graph that are connected and that contain this ringed cell and that only have 3 vertices, they're going to give us, well, they're basically going to correspond to the different 3 cells. So let's take a look at this situation here. So this is our 16 cell. This is the Wythoff construction of it. And then if we were to, say, remove this vertex here, well, this is a Wythoff construction of a tetrahedron. I should say, whenever we have 2 vertices that are linked and we don't label the edge, it should be imagined that it's labeled with a 3. So this is a 3, 3, this is a tetrahedron. So we could say it like that, or we could think of it a different way. We could say, well, these are 4 different symmetry operations here. And then if we just consider these, W1, W2, and W3, then what parts of our polytope are going to remain invariant under that? And it turns out in this case that the original tetrahedron here, when I say the original, it has to do with its positioning with respect to certain points, but like a sort of one of the tetrahedra is going to be held fixed by each of these symmetries. In other words, W1 won't change it, W2 won't move it, W3 won't move it. And so these are going to stabilize that particular 3 cell. The other 3 cell is this one, that's the other tetrahedron. Maybe this is a funny example. But then basically these, if we then look at the cosets of these groups, that's going to tell us about all the different vertices. So now there's more. Okay, so let's let's change channel a bit. Let's go back to thinking about the triangle. So we could say W0, W1, that's a 3, circle that. This means triangle. Now, this one here, well, we know that this has a Schlafly symbol 3, 3, so it's got to be the tetrahedron. Now, we also know about the symmetries of these kind of shapes, and it turns out that AM is going to correspond to this graph, which just has n vertices all in a chain. And if we have this thing circled, then it's going to correspond to the n-dimensional regular simplex. So that's going to have n plus 1 vertices in n-dimensional space. And, you know, this is one of the things that we're kind of interested in. But let's just have a look at the triangle again, because what I'd like to do now, we've already described some connections with linear transformations and matrices and representation theory, essentially. So now I want to show another way of doing this kind of Wythoff construction. So we're going to focus on the A2 case here, 2 vertices. So it's this case. So it's really the triangle that we're talking about here. And what we mean by this is we're doing this Wythoff construction. So, how are we going to do this? We want to do this in a group theoretic way. So, okay, we can draw our picture. So, this is O0, O1, O2, W1, W0. So I'm going to work with these kind of pictograms here that are going to stand for different permutations on 3 element sets. So we've got that one there and this one here. Now I won't usually, but sometimes I'll talk about the vertices as numbered 1, 2, 3 like this. So we could say that this is the permutation that swaps 1 and 2, and this is the permutation that swaps 2 and 3. But I'd rather not speak about the numbers. We'll figure it out anyway. What we're interested in is composing these things together to get all the different elements. But now, what we're really saying here is that W0 and W1 together, if we use those and multiply stuff together in all the different ways, we're basically going to generate S3, the symmetry group of, of 3 things. The symmetric group on 3 of order 3. The set of all permutations of 3 things. Okay, because we've already seen this, right? So we have, that's the identity. We're going to get a virtual mirror there. Anyway, if we reflect the identity in this red mirror, we get 1, 2. We get 2, 3 up here. If we reflect 2, 3 in 1, 2, what's this is? We're doing this operation after this one. So if we start here, and then we go up there, and then nothing happens, So it's this one. Right, so we have these 6 elements here are forming this symmetric group S3. So we can say, okay, we've got the identity and these other 2 rotations. And then we've got these 3 reflections here. And these are our 6 elements, these are S3, and so then what we can say is, okay, we want to think of our vertex sets, because we've ringed this, so we want to start with O0, and let's look at all the operations that leave O0 invariant. Okay, so if we look at this picture here, O0 is this vertex down here, and we have these 6 different operations, and which of them leave O0 the same afterwards? Well, it'd be this one and this one. And which do those correspond to? Those correspond to W1, basically, or the stuff generated by W1. And so we could make this remark that symmetries leaving O0 invariant are those generated by W1. And I'm drawing it as a Coxeter diagram. Okay, but I mean, basically what I mean by this is this set here that has the identity, and it also has this operation. Okay, so fair enough. That they're the set of elements that, do they say they stabilize this vertex? But anyway, that's this set. And now we want to get all of the vertices of our triangle, because that's what we're trying to do. We're trying to do this Wythoff construction. So here's what we're going to do. We take this set H here, which is our sets. Well, okay, that would be the matrices way of looking at it. But yeah, we take this set H here, which has this permutation here and this one here, and then we see all the stuff that generates, and that generates all 6 of our elements. So that's going to be S3. That's going to be this set here. So this is H star here. This is what gets generated. And then we take this set here. We're going to call this sets V0. Okay. This set of stuff that left O0 invariants. Well, we take V0 and we're going to apply all the possible symmetries to it. Okay, so if we apply a particular symmetry to V0, for example, if we have O0 over here, which is really sort of corresponding to V0, well, if we apply this symmetry operation over here, we should get this vertex over here. So we could call this vertex the result of applying this 1-2 symmetry operation to V0. And this has an interpretation now, because this has an interpretation in terms of left cosets. Because we really mean that we're going to multiply this group element here by this subgroup here. This is a subgroup of our symmetric group. Of this symmetric group S3 here, we're looking at subgroups of it now. So this is one of our subgroups, is this V0 here. This is the set of symmetries of the triangle that are leaving this vertex O0 invariant. And the interesting thing now is that if we apply this symmetry here, which is, we're basically doing this. So if we apply this symmetry here to V0, then we interpret this as is normal in group theory in terms of left coset. So what we're going to do is we're going to look at this set, but we're going to multiply this thing that we've just put in on the left by everything there. Group multiplication thing. And so what does this result in? Well, that first one, that's just this, isn't it? Composing with an identity won't do anything. For the second one, okay, if we start here and then we go up here and then we do this, then nothing happens. So it better be this, I guess, this rotation. And so it's this set here which is going to be corresponding to this vertex here. So that's what this is. And you can see that actually these are the set of symmetry operations which would move this vertex O0 over here. And so this is a sort of good name in a sense for this vertex here. And in a similar way, this vertex up here, we could say, okay, it's going to be this element here times by V0. So this is going to be another left coset here, but it's going to give this vertex. So that's how we can refer to the vertices of this triangle. The other part of this, if we have another look at the diagram, what we can do is ask ourselves what kind of connected subgraph having k vertices that holds the ringed vertex can we form given this structure. Well, in this case, let's say that k is 1. Well, then this is our only thing that we can do, is to delete W1 here. So we can take this original graph here and we can delete W1. Now geometrically, this is going to correspond to an edge. And the point here is that we're thinking about W1 and we're thinking about the symmetries that can generate, and we're thinking about what's stabilized by that. And so, okay, this corresponds to an edge, basically. And what's going on here is that we're looking at W0 now as our symmetry operation, and we're looking at what gets stabilized by that. Now, we know that it's going to be a one-dimensional thing because the connected component of our Coxeter diagram has one vertex. Okay, so we're going to see more examples of this later. That'll make more sense later with that remark. But if we take another look at this picture, we can see that this W0 here is leaving this edge here, which I'm going to call E tilde. It's leaving E tilde invariant when we do W0. So what is the group that's generated by W0? Well, it's going to involve having W0 itself, which is just this 1-2 swap, and the identity. And those are just the symmetry operations here, which are the ones of all of these 6. They're the ones that are leaving E tilde invariant here. And so we could call this particular thing, we could call it E0. It's like the fundamental edge. And then each of the other edges of the triangle is going to be of the form GE0, where G is an element of, well, basically S3, okay, the set of stuff that gets generated. So these are again left cosets, and these are corresponding to the different edges. And if we have a particular edge, we can work out what the vertices of it are going to be, because like we have to do this G operation on the fundamental edge. And so if we know which vertices the fundamental edge has, when we do this symmetry operation, we can just do that on those vertices. So it's how to express these vertices in terms of the original stuff. But basically what we can do is just have a look at the edge and have a look at the symmetry group for it and apply all those symmetry operations to the to V0, and then that's going to fill out the vertex set of this original edge, and then we can see what happens to it when we transform it around. But we can also match all this up with the matrix stuff. So that's pretty much the end of what I wanted to say. The DN case also, I showed the tables for E6. Let's just show the other ones. No, I showed them for E8, sorry. For E6, right, this is the similar thing. So this is how the nodes are labeled, and then the different rows of this give these different alpha I vectors that we can use to build the hyperplanes. For E7, this is a similar story, and I showed it for E8 earlier. So the only case we haven't talked over yet is the AN case. So maybe I should say how that works. So yeah, I'm just gonna scroll through this on the screen slowly. So if people are interested, maybe I can go through it one page at a time. Because I'm not sure I have the time to talk through how the AN case works exactly now, but it's all written down here. So you can take screenshots of this if this kind of thing interests you. So I'm trying to relate it here with the mutation game of Wildberger. So there's more to say on this story, but it's surprising because in many ways the AN case is the simplest of all of the ADE cases to deal with, but geometrically there's something a bit frustrating about it, because basically the easiest way to talk about the AN lattice is as this set of n plus 1 tuples of integers that add up to 0. And so for some reason one's working in a higher dimension, and this has to do with, for example, an easy way to have three things that you can swap around in geometry is to look at, in 3 dimensions, at the 3 different coordinate lines, x, y, and z, and then you can think about permuting those around and things. And so in that sense, you can look at these kind of pictures in 3D, which is a good way to define a simplex. So it's also a good way to talk about the symmetries of these things. And the whole of the discussion of the AN lattice is, in some sense, it's, one should be thinking of it in 1 dimension higher because everything's just cleaner that way. But it's also possible to transform everything down to the plane, and this is what took me a long time to understand. And then this sort of culminated in this Mathematica code here, which handles the AN case. And so with all this, I think there's finally enough to be able to make a sort of code where one could just click on these Wythoff constructions. So you can have like a picker and select a particular ADE graph and then which of the vertices should be ringed. And then this is going to lead to it generating the polytope, because now we can generate the vertex coordinates, and also we can generate the combinatorial structure. I mean, I haven't discussed fully about these cosets and things. It's better described in Coxeter's book, Regular Polytopes, as most of this stuff is. I feel like I'm still um, getting to grips with this, but I think with this connection with the matrix representations, things are working a lot more easily. And this particular Mathematica code that I just showed is also interesting because it ties in with the mutation game, because there's a way of doing all this with the ADE stuff, at least via the rotation game. So yeah, that's it.